Hello. Hi, everyone. Welcome to CEDAR 2023. It is exciting to see you all. My name is Goncharenko. I'm one of the two CEDAR student representatives on the CEDAR Science Steering Committee. This is an exciting day for Andrew and me. We have spent the past year putting together the student workshop based on your feedback from last year. So every year, Student Day is one of the most highly attended sessions at CEDAR for both students and scientists. The goal is to prepare students for the rest of the meeting and provide a reference for further understanding by introducing research tools and equipments, provide students and the rest of the community with an introduction or even reminder of the underlying facts and assumptions of various topics, and giving students a kickstart for the rest of the workshop. So without further ado, I would like to introduce the other student rep, Andrew Pepper, and my term is ending this year, so any nominations for the new student rep would be highly welcomed. And Andrew will continue on for another year, and he will present about the Student Day plan for this year. Okay.
Thank you. Thank you, Zishan. Good morning, everyone. Welcome to the CEDAR 2023 workshop, and welcome to Student Day. We have a nice place to be in, sunny San Diego, and we're very excited to share with what Zishan and I have been working on for the last year. So the theme today is going to be CEDAR student dynamics, and the goal of the workshop today is going to be to show students the multitude of career options and research options that they have in the field and community, and then show also what new opportunities you can look forward to in terms of instruments and modeling, and also navigate your young careers through the many trials and tribulations that you're going to face throughout your time as a CEDAR student. So what all does it take to be a CEDAR student? It takes a lot. We're going to be tackling complex physics, chemistry, and engineering problems. We're also going to be utilizing the latest instruments, models, techniques to answer and solve those problems, maybe. You're going to have to write papers, grants, and proposals, as well as take care of your own mental, physical, and health, and make sure that you have your personal relationships in line with your professional ones. So it's a lot of things going on in one student. And then, of course, you're managing new experiences and places as well. I don't know, perhaps you've been to San Diego before, perhaps not. So we have a jam-packed schedule today that I cannot wait to show you. So we have this broken down into three separate sections, and we're going to start with our lightning round tutorials, which are going to be in-depth physics and engineering problems presented to you by industry leaders and the community experts. The text might be a little small, but we have wonderful presentations coming for you. In our second section, we're going to be talking about tutorials and opportunities, and we're going to hear from the NSF, also from the DoD. We're actually going to do that first. And we also have some tutorials from the NASA CCMC and Super Darn Committee, as well as the ISCAT 3D. And then, of course, we have community engagement. So as students, we need to kind of band together and tackle the issues that we're going to face. So we have plenty of things from DEI center activities to an outdoor activity, which is across the street into the park. And we're going to end the day with a DEI tag up. I also want to recognize the student co-convened sessions that are going to be occurring during the week in this workshop. We have 6 of them, and you can see that they're sprinkled out throughout the schedule. So please stop by and make sure that you give credit and your attention to the students that are helping with these sessions. So since we have very short presentations in the lightning round, they're only going to be about 15 minutes. So in order to make sure that they keep moving quickly, we're going to be using Slido for that. So please, if you have a cell phone, I don't know why I said you have a cell phone, pull it out. Please go to this link so that you can ask questions, and make sure when you ask your questions that you address the speaker so that we know which one the question is oriented towards. Give everybody a couple seconds to do that. Okay. Still see some phones. Okay. Thank you, everybody. And we also have some other student activities besides Student Day, of course, that we're going to have throughout the week. So there's 4 main ones that you can look forward to. The first one's going to be tomorrow, the Mentor-Mentee Lunch, which will take place, I believe, in the porthole room. Excuse me. And those are going to be your opportunity to sit down and get mentorship from experts in the community and interact with them and whoever you desire to, which is going to be really awesome. We have a wonderful list of mentors signed up for that and students as well. We also have our poster sessions, of course, and those are Tuesday and Wednesday. So please go support your fellow students when it's not your particular day. And we also have salsa dancing on Tuesday. That should be very fun. And student lunch on Thursday, which will be innovative ideas for the workshop. And the 2 QR codes I have here, the top one is going to be the WhatsApp group. So when you are, not in a session and you want to communicate with students, please, that'd be a wonderful group to do so. Also, nightly activities as we go out and have fun with each other. And the bottom one is going to be the CEDAR Science Slack. If you're not a part of that, please join in. Okay. Thank you, everybody. Okay, I'm just going to leave that up here. So without further ado, I think we should get started and introduce our first speaker for the day, who is Dr. Larissa Goncharenko. Dr. Goncharenko graduated from Kharkiv Polytechnic University in Kharkiv, Ukraine, where she worked for 8 years before continuing to the US to find work as a postdoctoral fellow at the Haystack Observatory in 1996, where she still works today. Her research interests include stratospheric, mesospheric, thermosphere, and ionosphere coupling and space weather. She utilizes ground-based and space-based observations from ISRs, GNSS receivers, and ionosondes in her investigations to develop scientific endeavors. Without further ado, Dr. Goncharenko.
Thank you so much. I think we can take microphone and I have this one here. And thank you, Andrew. Greetings and welcome to San Diego. Welcome to CEDAR. As Andrew said, I've been around quite a while. I think this is my 27th year at CEDAR. And every time I go to a meeting and to any meeting, like large meeting like AGU, and I think I know everybody. And I now look at you and I don't know you. And I'm really excited and really enthusiastic to get to know you and welcome you to the community and to really be amazed by your all your talents and everything what you can bring to the field. So welcome to CEDAR. CEDAR is a meeting and CEDAR is a community. I was okay, it doesn't advance as I was hoping. Okay. It is on. It is on. Okay. This. Okay. Okay. So, sorry. First presentation takes time to figure it out. So when we talk about CEDAR, we talk about CEDAR in 3 different ways. First, and most of all, CEDAR is actually an NSF program, which is focused on understanding mesosphere-thermosphere, ionosphere coupling. But CEDAR is also a research community that includes hundreds of scientists with really significant international outreach. And another word for CEDAR is annual workshop, like what we have right now. And at this workshop and in general our activities, we focus not only on NSF supported portion, but also on interactions with other agencies and other collaborating with other people on both national and international level. Important part about CEDAR that it is a workshop. It's not supposed to be like just a long meeting with presentations, but it's supposed to be place for discussions. And we always try to keep it in this, to keep that spirit of CEDAR. The main of CEDAR is understand fundamental properties and space-atmosphere interaction. Again, it is centered on mesosphere, thermosphere, ionosphere, but huge topic in CEDAR is coupling to other regions, coupling to below, to troposphere, stratosphere, but also coupling to above, to magnetosphere, sun. CEDAR as a community, again, focuses on mesosphere, thermosphere, ionosphere, and there are other sister communities. GEM focused on magnetospheric connections, and SHINE focused on sun and solar studies. So when people think about this studies in heliophysics, it's really like three main pillars, and CEDAR is one of them. CEDAR, GEM, SHINE. And again, a lot of science research that we do is coupling studies. So we always try to be flexible. All boundaries are really relevant, really flexible. One really important thing to understand that CEDAR is very diverse community. We have people who focus on development instruments on development of new technologies. It is some portion of community. And when you look just examples of list of what kind of instruments people develop, you understand it's very different techniques that are at different stages of different advances. So there is huge diversity just there. Other part of community focuses on is purely theoretical, focuses on development of model. We have a number of people who work on that. But largest part of community is actually users, people who use both data and models. So regardless of if people started with instrument development or started with model development, but this is where we all converge. We try to do the best science that we can do with all the tools that we have, with all available instrumentation and all available models. A little bit about how CEDAR operates as a community. This is a grassroots effort, which means that CEDAR is a community of scientists run by scientists for the benefit of scientists. We have steering committee that has between 12 to 18 elected members, depending on some tasks that are around that term, and this is for 3-year terms. People roll out after 3 years, and committee includes representatives from National Science Foundation, international representatives, liaison to GEM. What is important? We want to hear students' voices. We always have 2 people on the steering committee from student representatives. Right now, every year we call for another nomination. So please, this is your opportunity to hear students' voices heard. Some other comments what I wanted to make. I assume that for a lot of you, this is your first meeting. For how many people are first time at the CEDAR? Can we show hands? Well, a lot of people. So I am not sure if you spent sufficient time studying agenda and trying to figure out what is it that you want to do. But I wanted to explain a little bit what you can expect at the workshop. So there are 3 major components. So in this meeting structure, 3 major components: plenary sessions, individual workshops, and poster sessions. And for plenary sessions, we have really mixed plenary sessions are every morning, and with the idea to present topics that are of interest to the entire CEDAR community, regardless if you're working with instrumentation or model development, but this is what we really want people to be aware of. So this include prize lectures and science highlights. We have, in particular, we have science highlights. We have several science highlights from mid-career scientists, but we really try to make an effort and highlight early career achievements. So we have several talks from early career scientists. We invite updates from international community. We'll have a couple of updates about ISCAT 3D and International Meridian Circles project, and updates on the upcoming missions. And on Thursday, we will have DI topics. There are 36 individual workshops with 3 or 4 running in parallel, which can be really overwhelming. So important, if you have not looked yet exactly at the agenda, and look carefully and try to figure out which one will be most beneficial for you. And you will miss some of the stuff that happens at CEDAR, and it's okay, because you cannot clone yourself, you cannot be in 4 places at the same time. If you are not sure, coordinate, ask your advisor, ask somebody you know for advice, but try to get as most benefit from this meeting as you can. Poster sessions, huge amount of posters on very different topics. One part on Tuesday is focused more on mesosphere, lower thermosphere coupling studies, another more on ionosphere, thermosphere, and other type of studies. I should say, every year I go to many different meetings. CEDAR poster competition is student poster competition is most comprehensively judged meeting that I've ever seen, and it is consistently year after year after year. So for people who receive CEDAR poster award, it means that this was thoroughly judged by a large group of people, discussed several times with a group of judges. And we really try to provide feedback to people how you can improve your presentation skills and how you can improve your science. We have 2 town halls in SF and NASA. We have banquet and presentation on Thursday night. And this is just example how you can participate. Presentation is by graduate student from Vincent Lidvina from University of Alaska. Is Vincent here? Hey. Hello. So large agenda, lots of very exciting things. A lot of them will go over your head, and it's okay. Important thing to remember that it's okay if you do not understand a lot of it. You will get there eventually, and it's okay to get overwhelmed, but still try to get as much as you can from this meeting. How you can get the most of it? Try to be as active as you can. We already talked a couple of times, Andrew and I, about volunteering as student representative. Volunteer to help convene a workshop. We constantly ask conveners to invite graduate students and postdocs. And Andrew just said we have 6 workshops out of 36. That's actually not sufficient. Some actually, in addition to that, we have postdocs running or helping, but we would really love to students participate more in organizing and running workshops. You can, when you see a workshop which is a topic which is of interest for you, volunteer to present at that workshop. Again, for this year, agenda is already set, but remember for next year, do not be shy to write conveners and say that you're working on a topic which is appropriate for this workshop. Use opportunity to attend town halls. NSF is really open to, excited to hear about you. People arrange this workshop. NSF and NASA arrange these town halls because they want your participation. They want to hear from you. They want to hear your concerns, your questions, your ideas. So participate. This is a great opportunity. What it all comes down to that, start forming your own professional network. Meet fellow students, meet early career people, mid-career people, meet representatives from funding agencies, understand where you are, try to understand where field is going. The worst thing what you can do at the CEDAR workshop is stand near your own poster and after this go back to a hotel room and order pizza. Don't do that. If you see that something you think is missing, something that could be improved, don't be too shy. Suggest your ideas. Come to organizers, come to steering committee, come to student representative, come to any member of steering committee. Come with your ideas, and we're always happy to hear from you. Something I wanted to bring up as I was looking at the agenda. We always deal with different challenges. And some of them are older challenges, some of them newer challenges. We always try, usually it's at science meetings, at workshops like this, we try to focus on our science. But we do live in a society with, and we cannot be free from all the difficulties of this society. And some of the major challenges that they're kind of their long-term, but really more concerning right now with actually place of science and academic research in United States with funding for academic research, and in particular with retention of early career researchers. So for lack of funding was a problem for quite a while. We all know this. But and low salaries for graduate students, for postdocs, but with a crunch of high cost for housing, and with another long-term problem, daycare system, which is in absolutely horrible shape in the United States compared to other countries. So early career researchers are in very difficult situation, and we. Society understands this, and people talk about this more and more. I put here just couple of examples, just from last several months, and it's something that we did not talk like 10 years ago. We did not talk about graduate student unions, and now people are talking about it actively. We did not talk about strikes several years ago. And we'll hear a presentation today and about University of California in December. Here's an example from December when people were talking about this. It's not something that I wanted to do. I wanted to go back. Yes, when it was 48,000 people going on strike. Just in June, like by mid-June, another strike was ended at University of Washington. And the result of that strike, that salaries of researchers increased by 33%, seems huge, right? But when you look at what was minimum salary before that, you understand that you simply cannot live in that area with this type of income. So again, there are big problems, and there are no simple solutions. Because even if increases in graduate student salaries and postdoc salaries, even if they are mandated by some institutions, question is, where does that money come from? Because we do not really have high inflation is everywhere, and but our funding agencies do not really have proportional increase in their funding. So if we would hear from Ellen, if Ellen would come and say that we have increase in 30 to 40% for NSF funding, I would be happy to hear that. I would know that, yes, we can increase salaries for postdocs and graduate students, but Ellen is not in that situation. Unless I'm not aware of that. Okay, again, my point is that depending where you live, in some areas, especially on the East Coast and West Coast, this is more significant problem compared to other areas. And again, meeting is a place where you can get together, exchange some ideas, and see, maybe learn how other people are dealing with situation. And I will be happy to talk more about this if people are interested. Okay, something I really sad to bring up, but we do ask, we did send email and we do ask people to think about COVID precautions. Community had concerns after last year's meeting when, and we do have vulnerable people in the community. So please, especially when you sit in one room for several hours, transmission can happen. So please remember that conferences are still a high-risk environment, and take precautions during travel, take precautions during meeting. And if you're not feeling well, try to get tested and isolate, and just follow precautions. And I think this was my last thing that I just wanted to call to your attention. But main thing is, welcome. We are really excited to see you. It's exciting time to learn from everybody and communicate, share your advances, learn about other people's advances. Look to the left, look to the right. These are people who will be in the field 10 years from now. Get to know them, make friends, and enjoy. Thank you.
Oh, thank you so much, Dr. Larissa Goncharenko, for the very nice opening talk. So our next speaker is Captain Nick DeShannis. Captain Nick DeShannis is a captain in the United States Army and graduated from Johns Hopkins University with a Master of Science in Electrical and Computer Engineering in 2021. Since 2016, Captain DeShannis has specialized as an Army Space Operations Officer assigned to various roles, including the United States Army Space and Missile Defense Command. Following his post with the USASMDC, Captain DeShannis was assigned the role of a Physics II instructor at the Department of Physics and Nuclear Engineering at the United States Military Academy, and has traveled here today to talk about some of the DoD opportunities on the horizon. Okay, thank you.
Thank you.
Can you hear me? Whoa. You can definitely hear me because I can hear me. So y'all did your back work here. I didn't tell them any of that. Who have you been talking to? Appreciate it. That was very nice. Yeah, so like she said, I'm a captain in the Army. Colonel Loucks over here in the front's my boss, so please say nice things about me. But yeah, so I teach Physics II. I'm actually going to be the course director for a new course we're teaching called Introduction to Space Sciences at the Academy, where we're trying to kind of teach electricity and magnetism, but instead of a circuits perspective, we're going to teach it from an ionospheric perspective to kind of modernize how that's taught in academia. But yeah, and so on the other note with that, I do a lot of research in the ionosphere with Colonel Loucks. We do a lot of work up at Poker Flat. We're developing a sounding rocket program to try to study the ionosphere up there. And what we're really looking into is kind of the effects. And the talk that we just had where it said, you know, the biggest participants are those who use the data. That's us. That's me, right? Like we use a lot of this data. We do some research, but we have to use it in order to be effective. And so what we do is we figure out how do those effects that y'all do research on, how do those actually affect things like the GPS in your phone, right? The scintillation and how that causes errors And that's a big concern to the Department of Defense and the US military. And so what I'm going to do is I'm going to kind of show and go over a little bit of what we do at the military academy, but also what the DoD writ large does with all kinds of space and yeah, no worries. I'll just keep talking. But yeah, what the DoD and military does overall to study this stuff at all of our academies, at our postgraduate schools. And the one thing that we are going to get next year is the research labs as well. And so that's what I'm gonna kind of go over today. Nailed it. We good? No worries. You said it's not working. It's all right. So I think this is just like a military joke because they do this to us all the time. Usually they just give us a microphone and it doesn't work. So you just like yell at people. And then some guys in the back's like, ha, gotcha. All right. Yeah. So we're going to go over all the different service academies, kind of go over some of the research that we do. And then we're going to go over the graduate schools and some of the military units that actually use this data that we do research on. So first, obviously the best is the United States Military Academy. I have no idea why I say that, but it's true. And we do a lot of research, like I was talking about current aligned fields, where they do the reconnection, a lot of research into that. Like I said, we're starting a sounding rocket program. I actually have a cadet up at Poker Flat right now, trying to do a feasibility study with the Geophysical Institute at the UAF, University of Alaska Fairbanks. And then also working a lot with NASA and kind of modeling how they do this. On top of that, we also do a lot of stuff at Poker Flat with trying to predict the plasma flows and stuff like that. And I guess the whole point for all of you is like, how many of you are trying to get a job soon? Yeah, me too, right? Like I want a job. And so I'm showing you all this stuff. So there's a lot of other opportunities besides just staying in the academia world. You can actually affect operations, but you can also do both, which is kind of what's cool about the academies. We do a lot of research on all this. And what's interesting about the academies is if you get in a job like doing something like this, you don't have to like commission and wear a uniform like I do. Like you can do whatever you want, really. You could just be a civilian or a contractor doing this type of research. And that's really awesome. We actually just hired a Title 10. We just hired a Title 10 who's going to help with a lot of this research. And so those job opportunities are there, especially at all the other academies too, not just West Point. And what's really interesting is like the amount of impact that you have on these kids is phenomenal. You can show them what you do. You can show them what being a leader and what a scientist truly is all about, and inspire them. And you get a lot of freedom with that. One of the postdocs we just hired, she does high energy lasers. She runs her own lab. First job after her PhD, runs her own lab. Has full autonomy and does great work. Really, really incredible. So if that's something that's interesting to you, I would go to USA Jobs, and I'll show you that at the end because there's a lot of opportunities. Like I said, other things that you get to do is we try to find new innovative ways to kind of always be ahead of our peers, right? And competition and winning matters and things like that. And so getting these students understanding the things that you all understand in this room at this conference, we're trying to do that at like the sophomore freshman level, which is not easy, right? Plasma physics tends to be difficult. So that's one of the jobs that I have. I'm trying to actually do that. I'm trying to teach, like I said, electricity and magnetism from that perspective. So that way they're more innately familiar with this environment because it has a lot of effects on our modern way of life. Yeah. So then the Naval Academy, meh, right? No, they do a lot. Just saying. That's actually probably not a good idea around here at these parts. There's a lot of battleships out there. I could take them. Anyway, so they focus primarily on CubeSat research. So they have a lot of CubeSats, and they have their cadets going in and like kind of building like this USNS 16, the PSAT 3, BrickSat, doing radio radio transponders and amateur radios, ham radios. They also do a lot of stuff with like how these microsats and CubeSats can sense and do predictions of the ionosphere and stuff like that. So they have a huge program that's coming about that's getting pretty seasoned. And they do great work over there in Annapolis. And then you have the Air Force Academy in Colorado Springs. Pretty cool place. This institution differs from West Point in a little bit. So at West Point, everything is kind of run by the cadets, which is weird. We give them like free reign, and it's amazing. Seeing it, like they get so excited and they just show you everything that you couldn't even think of. At the Air Force Academy, it's a lot more structured with their civilian counterparts. So there's a lot of civilians and contractors who work in these labs and kind of help them progress. And that has some benefits and not some benefits, right? So for the cadets that are actually doing the research, it's much more structured, but they also have longevity in this research. And so they do a lot more like actual missions and launches aboard the ISS or anything else up into space. And they do a lot of research as well in the ionosphere. Colorado Springs ain't a bad place to live. Was there for 3 years. Pretty sweet. Can't go wrong. Okay, now we have our graduate school. So the Naval Postgraduate School. This is actually pretty cool. So they just did their space weather research and launched this, I believe, back in 2019, the NPSat-1. That was basically a vehicle to do space systems engineering, which is not really what we're all here for. But one of the main objectives here was to provide the platform for space weather experimentation and ionospheric physics. And so that is a huge project and a huge source of income and research that the Naval Postgraduate School is doing. And it's all led by postgraduate students. It's actually really amazing. So the Naval Postgraduate School, what that is basically, that's where people in the service, primarily the Navy, weird, they go in Monterey, California to get their master's degrees or PhDs. So that's an opportunity for you to further your education or to even go work and help do some of this research. And some of the stuff they do that's really cool is they have a lot of classified research that they do there. So it's one of the universities that they have like their secret and their skiffs and stuff like that to do government research. And so once you go down that rabbit hole, it's kind of hard to come out. Pretty exciting. Then you have AFIT, the Air Force Institute of Technology. Their slogan, I guess, is sun to mud, but they end at the ionosphere. So I'm not really sure what they mean by that, but it sounds good, right? But they do a lot of solar physics and then basically that entire transport model all the way back to the ionosphere and how it interacts with the ionosphere. They do a lot of CME research. And I actually forgot to mention that we also do a lot of CME research with Johns Hopkins. We're using the Parker Solar Probe to basically use those measurements to model CMEs in a 1D transport model back to the Earth. And AFIT kind of does something very similar. All right, and so from those graduate schools, we now have actual operational units, and these are other places where you can work. And this is where you're not doing so much of the research, but you're using that data, like was said, and you're providing products to help paint that picture for the operator, for the people that are actually conducting operations all over the world. So the 2nd Weather Squadron is under the Air Force. And what they do is they basically provide all different types of space weather and terrestrial weather. And they provide these reports, and you can kind of see them in the bottom right there. And those tell us like what kind of communications we can use and what we can't use in that region of the Earth. Typically SATCOM, but they do a lot more than just that. They show scintillation, they show GPS error. They're going to show like snowfall covering the Earth and like how that's going to work. They're primarily focused on terrestrial, like land-based operations and air, but the FINMOC, and if there's anyone in the Navy, I'm sorry to say this, but the FNMOC is what everyone not in the Navy calls it, because it's hilarious. But they basically do the same thing, except they're focused more on the oceans, right? And so they do a lot of atmospheric data, ice depths, ice charts, wave heights, wind speed charts, ducting effects, and how that affects radars and stuff like that, which is kind of a primary part of our national missile warning structure. They do a lot of stuff in the Arctic region with ice predictions, ocean global temperatures, and how those all kind of affect basically any maritime operations and trade routes and stuff like that. Close partners with NOAA as well. So if you were interested in any jobs like this, the military is in need, right? We need a lot of people just like you, all these smart and enthusiastic researchers, to help us and do some of this research with us and give us some of your expertise, because all of you are doing really amazing work, and we want to capitalize on that from a national perspective. So USA Jobs is where you can kind of go in and find this market. And what I would recommend is, if you go in here, this first thing, the keywords, just type in like whatever you're interested in, right? Space weather, ionosphere, physics, plasma, and it'll show you where all these jobs are listed and what's available for you if you want to go into anything like that. But with that, I think that's all I got.
Thank you, Captain Deschanez. Okay. So our next speaker is going to be Jonathan Rizzo. Jonathan is a former electrical engineering student who graduated from the University of Scranton in 2021. While not in academia anymore, Jonathan's research interests that he discovered with his former advisor, Dr. Nathan Frizzell, have since led him to perform science research projects as a hobby. He's uniquely interested in the VLF radio phenomena called natural radio emissions, which occur as a result from lightning discharges and solar wind interactions with the magnetosphere. He is coming to present to us on that unique interest and hopefully inspire students to pursue their own research projects in graduate and professional life.
Hi, my name is Jonathan Rizzo, KC3EEY. I'm a VLF natural radio enthusiast and electrical engineer. I'd like to introduce VLF natural radio. Sorry about that. I would like to introduce VLF natural radio emissions, provide some examples with audio samples and an automated VLF reception system that I installed in northeastern Pennsylvania as a citizen science effort. Oops, let me just move this here. The very low frequency band lies between 3 kilohertz and 30 kilohertz. The ultra low frequency band lies between 300 hertz and 3 kilohertz. VLF ULF propagation behavior is similar to propagation through a waveguide due to the spherical waveguide formed by the ionosphere inert surface, commonly referred to the Earth ionosphere waveguide. Naturally occurring radio emissions from lightning discharges and magnetospheric plasma interactions can be detected in the VLF and ULF bands. Because these radio emissions occur at mostly audible frequencies, they can be converted directly to sound and listened to as they are. Here's some examples of VLF natural radio emissions. One example is radio atmospherics, or more commonly referred to as spherics, generated by lightning strokes. They're the most common type of VLF natural radio emission, and they're very broadband and impulsive in nature. They occur almost constantly, can be detected anywhere on Earth. Lightning detection systems use spherics for lightning location using the time of group arrival method, or at least some of them do. On the right is a spectrogram of spherics captured in the summer of 2013. A spectrogram plot is a plot of frequency versus time with intensity represented in color. Here's an audio sample of what they sound like. Well, hopefully I could get this to play. Some spherics have their frequency components dispersed in time due to resonant modes of the Earth ionosphere waveguide and are called tweaks or tweak atmospherics. Frequency dispersion occurs at around 1.7 kilohertz and multiple harmonics thereof on the scale of milliseconds with longer dispersions at night. They have a distinct pinging sound. On the top right are spectrograms of tweaks recorded in the summer of 2013. On the bottom right are tweaks recorded in January of 2022. Here's an audio sample of what they sound like. Notice the pinging sound. Another natural radio emission is called a whistler. When spherics propagate out of the ionosphere, they can take a propagation path thousands of miles through a duct that forms in the magnetosphere, as illustrated on the right. This duct consists of solar wind plasma that has aligned itself along one of Earth's magnetic field lines. As the spheric propagates through this duct, its frequency components get dispersed in time, ranging from less than a second to a few seconds. Lower frequencies propagate slower than higher frequencies, so higher frequencies arrive at the endpoint sooner. Since these ducts follow the Earth's magnetic field lines, the propagation path terminates in the opposite hemisphere. The frequency dispersion produces a long wavering tone that is characteristic of a whistler. This propagation mode is often called whistler mode propagation. The electron density of the duct determines the amount of frequency dispersion called dispersion measure. Whistlers that have a very discretely sounding frequency components are called pure note whistlers. Whistlers can sound breathy or swishy and have more diffuse frequency components. From the perspective of the terminating endpoint, the originating point is located at the geomagnetic conjugate, as illustrated here. Here's an example of what they sound like. On March 10th, 2023, there were some whistler events that occurred a few days after some strong geomagnetic storming in northeastern Pennsylvania. Here are some examples of those whistler events. As seen in the spectrogram, these whistlers do not have long frequency dispersion, but are also pretty diffuse. But they were pretty strong and audible. One question worthy of investigating is how strong geomagnetic storming influenced the electron density of whistler ducts, resulting in the short frequency dispersion. Hopefully this is loud enough. This is a histogram plot of whistler count data for a location in northeastern Pennsylvania from December 2021 until March 2023. As you can see, there's an uptick in whistler events during both early spring and fall months. This raises some interesting science questions worth investigating. How much of the conjugate points climatology had an influence on early spring and fall whistler counts? How much of an influence did geomagnetic activity have in creating and enhancing ducts, and how did this affect the whistler's dispersion measure? Using data from a network of VLF receivers can help answer some of these questions. When solar wind interacts with the magnetosphere, emissions are produced due to cyclotron interaction called dawn chorus. Dawn chorus emissions are discrete events that often overlap and are spaced closer together. These emissions often sound like tree frogs or peepers and much resembles birdsong at dawn. It often occurs during geomagnetic storms and in the early morning hours of dawn. Discrete dawn chorus events can be spaced out on the order of a few seconds or more, and these are called periodic emissions or risers. Dawn chorus can also occur during auroral display events, and this is called auroral chorus. It is possible to use a VLF receiver to listen to auroral chorus while watching an auroral display. Here's a beautiful dawn chorus event that occurred April 10th, 2022, during a G7 geomagnetic storm in northeastern Pennsylvania. It's a 3-hour-long event. Its frequency components extended up to 5 kilohertz. This dawn chorus event had quite a large footprint because it was also detected at a VLF receiver in Forest, Virginia. Notice a horizontal alignment of spherics, which is made possible by GPS timestamping at both receivers. On December 27, 2022, around 4 a.m. local time in northeastern Pennsylvania, a beautiful dawn chorus event occurred during some weak geomagnetic storming. It was 4 hours long in total, with the peak intensity around 5 a.m. local time. What was unique about this dawn chorus event was how wideband it was, extending up to 7 kilohertz. It sounded absolutely beautiful. It also had a wide footprint and was observed at a VLF receiver in Forest, Virginia. An hour later, or hour earlier, it was a similar event was observed in the UK. On February 27, 2023, during some strong geomagnetic storming in northeastern Pennsylvania, riser events were observed. Most of the amateur radio examples I've played were captured using the Whistler Catcher VLF reception system. It is comprised of a VLF active antenna and a Raspberry Pi backend system. My goal is to create documentation and kits so others can install these in their radio quiet backyards and create a global network of VLF receivers. Here's some pictures of the VLF active antenna installed at a quiet location in Springbrook Township, Pennsylvania. This is the inside of the VLF active antenna. On the left is a picture of the VLF Receiver Preamp board constructed using Manhattan construction. In the middle, you can see the board fits inside a circular foam insert. On the right, the E-field antenna is comprised of copper tape on the outside of another foam insert. The antenna wires solder directly to the copper tape and the front end input of the VLF Receiver Preamp. The foam insert used to dampen microphonic vibrations due to wind. The feed line and earth ground connection attached to the green the green screw terminal connector. Everything fits nicely inside the PVC pipe. This is a high-level schematic of the system. It illustrates the front end and line driver of the VLF active antenna and electrical isolation between the preamp and back end using isolated DC to DC converters and audio isolation transformers. This is the Raspberry Pi backend system with VLF active antenna interface, primary power converter, GPS timing receiver, audio injector stereo sound card, and Raspberry Pi 3. Spectrum data is stored on a VLF thumb drive or on a USB thumb drive and is processed using VLF RX Tools software. It is also streamed to a local server for storage. Spectrum data is streamed over the internet to an aggregation server where you could listen to the VLF receiver in real time, look at captured events from the event detector, and see plots of VLF power spectrum. It is also streamed over the internet to a server at my home. I invite all of you to look at my poster for more information. It will be here tomorrow. Thank you very much.
Yeah, thank you so much, Dr. Rizzo, for the very interesting talk. It would be really cool to have a VLF active receiver in your backyard and do some citizen science. Okay, so I'd like to remind everyone that we will have a joint Q&A at 10:30 to 10:50. So if you would like to provide your questions on the Slido link, please do so. And also remember to vote your favorite questions so it would be firstly asked. All right, so our next speaker is Dr. Scott England. Dr. Scott England is a associate professor in the Aerospace and Ocean Engineering Department at Virginia Tech. He did his PhD at the University of Lancaster, UK, studying the coupling of energy and momentum between different regions of the atmosphere via atmospheric waves. He came to Virginia Tech in 2017 and currently focuses on using remote sensing instruments to study the upper atmosphere and near Earth space environment. He's a project scientist of NASA Icon spacecraft, a co-investigator on the NASA Gold spaceflight mission, and also a participating scientist on the NASA Maven mission to Mars. Okay, let's hear about Dr. Scott England.
All right, thank you. Okay, so I am going to cover thermosphere, ionosphere, magnetosphere coupling in 15 minutes. We're going to start from the basics and derive everything. So, I mean, I want to spend a minute on this. This is not intended to be comprehensive, right? What I'm going to give you is my own very biased lens on this, what interests me, what motivates me, and hopefully for some of you, give you just a little bit so that when you're in another more detailed talk later in the week, you go, I have some idea what this is about. And that's the spirit in which I created these slides. So here's the lens in which I look at this. So I'm going to view this system, this coupling, in a few different ways. We're going to start with the energy. We're going to follow the energy. Then we're going to look at the matter and follow the matter for a little bit. Then we're going to make the whole thing move, and we're going to look at momentum. Then we'll look at feedback. And throughout this, and this is an apology I'll get out the way right now, I've kind of pushed the magnetosphere to the end. I know that immediately following this, we have another presentation focusing on high latitude ionosphere. So I figured I can lean on that and hopefully just make this a segue into a much more detailed look at the high latitudes and how the magnetosphere really couples into this system. So I promised you energy. Let's start with energy, and I might draw a diagram, and if I was very clever, I'd draw a really complicated one like this, which I didn't draw. But this shows energy inputs and energy flow in this system, right? So our system is this green box, the neutrals, that's our thermosphere, and then the yellow and orange are ions and electrons in our ionosphere, specifically the ionosphere for this. Inputs, we've got inputs coming in from up above us, okay? UV radiation over in the corner. Coming in, and this can be going straight into the neutrals, it can heat the electrons. The electrons, ions, and neutrals can exchange energy and such. To give you some context, right? If I'm somewhere near the equator on a typical day, the UV radiation we're talking about in the extreme UV, there might be about 4 milliwatts a square meter. Far UV, maybe another 10. So we're talking maybe 15 milliwatts a square meter. If I look at some of these other things here, the energetic particles, those are coming in, that are dual heating. So we're getting this because the ions and neutrals aren't moving together at high latitudes. These can be putting in way more energy, maybe 60 plus milliwatts a square meter, but only in the high latitude region and in really complex patterns, which makes them really interesting. Finally, we've got some energy coming up from below in the form of waves, transporting energy through the neutral medium from lower regions of the atmosphere that are more dense and can have much more energy content. And then as energy escaping from the system, we can have infrared radiation going out. We can have conduction of heat going down. And you can build this, and you can build out these equations and view this whole coupling through energy balance. But it is remembering the matter that we're dealing with here. So if we talk ionosphere, thermosphere, magnetosphere, it's almost all neutral by mass. It's almost all the thermosphere. And the ions that are there in the ionosphere are being produced from those neutrals. They're recombining and going back to the neutrals. The magnetosphere is a little different, right? So some of those ions did come from the thermosphere, got ionized and moved their way out. Some are coming in from the neutral, from the solar wind. But a couple of processes, and I've missed off the energetic particles here. I focused in on UV for a minute, but a way that we're generating these ions, a way that they're we're getting this relationship between the neutrals and ions is because of, for example, the UV radiation. So the plot on the left, I know it's a bit small, but it shows you where radiation of different wavelengths are being absorbed. And if I look at thermosphere altitudes, I see it's this extreme UV, so stuff shorter than Lyman alpha or so, plus some of the far UV. And all these wavelengths are short wavelengths, high energy photons. So they have enough energy not just to be absorbed by an atom or molecule and heated up or knock an electron into a higher level. They've got enough energy to be breaking apart the molecules, breaking apart the atoms, releasing electrons, so overcoming the ionization potential. And there's some equations in the bottom corner that give you those and the wavelengths at which that happen. If I look at one of these, I could follow that process and go look at the diagram on the right and follow the energy again, which I'm not going to do. But if I think of it in terms of the process like in the middle, so I've got an oxygen atom being hit by an extreme UV photon short of 91 nanometers. And it's going to ionize that oxygen, produce an oxygen ion, which is the most abundant ion in our ionosphere, and an electron. But if I have a wavelength that's anything shorter than 91, then I've got some leftover energy. And on the right-hand side of my equation, I've got two particles. I don't generally have another photon coming out, right? So where does the extra energy go? And the extra energy goes into, it can go into excited states of that O+. It can go into kinetic energy of these two. And if I look at my electron, it's really light, doesn't have a lot of mass. And if I give it a little bit of kinetic energy, it can move really fast, way faster than it would take to escape from the Earth if Earth didn't have a magnetic field. But Earth does. And so here in the bottom picture, there's something really neat. What we're seeing here, this is an image from the Gold spacecraft. And on the right-hand side, that's daylight. And you can see the day-night boundary drawn there. So everything's on the right-hand side of the image is in daylight. And in the South Atlantic, it's daylight. In the North Atlantic, it's not. It's nighttime. And what's happening is in sunlight, some of these O+ and other things are being ionized, and electrons are being released with some extra kinetic energy. Enough kinetic energy to go way out into space, 2, 3 Earth radii, moving mostly parallel to the magnetic field line. They come slam back into the Earth in the North Atlantic, and you see that sort of light blue area there. They're making the sky glow at night. And this is the same sort of process we have happening in the aurora, but this is just happening in the middle of the Atlantic. It's pretty dim, but it's another neat way of looking at ionization and how all this stuff is coupled. Along with this, and we talked about this a second ago, if I'm looking at O+, I'm looking at my main ion in the ionosphere. I can produce it a few different ways. You know, I can ionize oxygen. I can break apart O2 molecules. And if I look at how I'm losing it, an O+ meeting an electron and recombining is hard to balance energy and momentum. So what tends to happen is instead the O+ collides with some molecular neutral, and we end up exchanging which one of these is ionized, and we end up with an ionized molecule that then can recombine by breaking apart. And so if I look at the life cycle of one of these O+ ions, I'll see that if I've got more oxygen, I've got a way of producing more of these. And if I've got more moleculars like N2 around, I've got a way of losing these. And so you'll see, hopefully in a bunch of talks throughout this meeting, people talking about this O to N2 ratio. And at some crux, this is what it's getting at, is just, it's a way of tracking, you know, how the composition of the neutral atmosphere is going to be impacting the production and loss of the ionosphere. All right, let's make the whole thing move. So we're going to introduce winds in the neutrals, and they will move in similar sort of patterns that we see winds in the lower atmosphere move. There's a couple of extra forces, frictional collision with the ions not being one of those. The ions, on the other hand, and the electrons don't want to move in the way that neutral winds are. They feel this Lorentz force. It's going to keep them really bound to the Earth's magnetic field. But these two fluids, let's think of it that way, right? Our neutral gas and our ions are colliding with each other. So a well-known and a neat system that happens at low and mid latitudes is sort of depicted in the left-hand panels of this. I will have neutral winds moving perpendicular to the magnetic fields. And they can move the ions with them. They tend not to move the electrons. You can think of this in terms of ratio of collision frequency and gyro frequency. You can also just think of this as an ion's a big target and electrons a really little target. And so if they're moving the ions, not quite exactly with the neutrals, but across the magnetic field lines and leaving the electrons behind, I've now generated a current. And that current system is drawn in the panel in the bottom. And anywhere I get divergence in this current, I can create electrostatic fields. Of most importance is this sort of eastward electric field at low latitudes. And I've got a northward going magnetic field, and I can generate an E cross B motion that's shown in that top panel there. I can measure this in that case with a Hickomarka radar and see an uplift of the plasma at low latitudes during the daytime. And what this does is it takes that O+ that we're producing in sunlight, moves it up in what we call a fountain effect. So moves it to higher altitudes and higher latitudes. And we form this two bands, this low latitude equatorial ionization anomaly. And I could have shown you all of those left 4 panels, maybe 10 years ago. More recently is on the right. So this is some results from the ICON spacecraft, which just had a 3-year mission before it failed. And what it was doing was zooming in on this process, and you can see depicted there in the colors in the bottom, measurements of the winds that are driving this system. And as the spacecraft's flying along, the wind pattern switches, and at that same place, this E cross B, this vertical plasma motion, switches direction too. And it gives you a way of really zooming in and looking at in way more depth at this dynamo system. We can pull back and look at large scale. We talked earlier about waves bringing energy up from below. Here's just one example, looking at a global scale wave pattern called an atmospheric tide. This wave feature has its origins in energy released as I turn water vapor into clouds down here in the lower atmosphere. So there's latent heat as I go from vapor to liquid. That induces a motion in the atmosphere, this wave motion that propagates all the way up. The winds perturb that dynamo we were just looking at and creates variations in this equatorial plasma and variations in the plasma drift you can see on the top right. And this, for me, this image, this set of images here, this is what got me hooked in this whole field. This notion that I can step outside and that rain that's falling on my head is somehow connected to the plasma 600 kilometers above me, or what's outside the ISS or something. That was it. For you, it may be different, but for me, this and this picture and this real coupling all the way from the troposphere through to the ionosphere really got me hooked in this. All right, moving on. The winds do other things. What we see in the lower regions of the thermosphere is a lot of regions of wind shear. So winds moving in opposite directions in 2 layers, just one above the other. And depending on the orientation of these winds and the orientation of the magnetic field depicted in those middle patterns, what this can do is cause vertical motion of the ions in the E region and kind of squish them together sort of into these little flat pancake layers. And then on the right-hand side is some work, looking at these winds and these wind shears and looking at how they stack up with a phenomena called sporadic E, or this is a way that concentrations of ions in the lower E region can interfere with radio propagation. Okay, we've been talking about, for the last few slides, about the neutrals driving everything, but the ions have an impact too. And that can be through a variety of things. So even if we stay at low latitudes, the ions can change the temperature of the neutrals and the density of the neutrals through collisional heating. So typically the ions electrons are much hotter. And if you could read the equations, and I know you can't on this projector, trust me, I can on my screen, you would see how it can get heating of the neutrals through collisions with the ions and electrons. They can also modify the winds. We've got this collisional term in the acceleration equation on the second line. So as the ions are moving differently to the neutrals, they can impart momentum to them. And we can see in the neutral winds sort of evidence of this equatorial ionosphere. Moving to the higher latitudes and looking at what the magnetosphere does in all of this, there's some pretty spectacular examples. So we're saying the magnetosphere has this ability to put a lot of energy into a concentrated region near the poles. When I do that in an event like a storm, I can generate a lot of heating in that polar region, changes in the winds and the circulation, bringing winds away from the poles, which will transport neutral species differently. You can see that in the bottom panels showing up in a change in this O to N2 ratio that we talked about a few slides ago. And seeing in this case, it really decrease in the polar regions as this wind starts to transport the oxygen essentially equatorwards. We can also get direct effects from the electric fields coming in from the magnetosphere, impacting that E cross B drift, which is what's shown on the right-hand panels, and changing that equatorial fountain. If we look at the high latitudes for a minute, and I'm not going to spend too long on this because I know this is the focus of the next talk, but we have this complicated system of ingoing and outgoing field-aligned currents. And these close with horizontal currents flowing through the ionosphere. And we get heating of the neutrals in that region because the ions are moving relative to the neutrals. We get this strong Joule heating. And we also get this acceleration of the wind again, because our ions are moving relative to our neutrals and these two are colliding. And just one final example of that. If I put a lot of heat and momentum in the high latitudes, it's a little bit like if I take a pool of water, it's all static, everything's in balance, throw a pebble into it. And the way the system reacts is that it radiates that away in the form of waves. And what we're seeing here is some examples of observations of waves moving through the thermosphere and through the ionosphere away from those polar regions in response to that energy input from the magnetosphere. And then I will end with a slide showing you where I stole all those figures from.
Thank you, Dr. England. Okay, once again, thank you, Dr. England, for that wonderful presentation. And next up, we're going to have Dr. Megan Burleigh. Dr. Burleigh is a research scientist at the Naval Research Laboratory in Washington, D.C. She obtained her PhD in engineering physics in 2018 from Embry-Riddle Aeronautical University in Dayton Beach, Florida. Her research centers on studying the Earth's ionosphere as she focuses on high-latitude magnetosphere, ionosphere-thermosphere coupling with data-driven, data-inspired, and parametric physics-based modeling at global to local scales. She's an active user and developer of several ionospheric models, such as GITM and the Gemini modeling suite, and routinely works with data from incoherent scatter radar, sounding rockets, and satellites. Welcome, Dr. Burleigh.
Thank you very much. I think that introduction made me sound way cooler than I feel. Yeah, thank you everyone for the opportunity to be here today and talk to you about the high latitude ionosphere. As Andrew had said, my name is Megan Burleigh. I work at the Naval Research Lab. I learned something today about FENMOC. Thank you. So I should blame my brother? Alrighty, to give everyone just a brief overview of the high latitude ionosphere. The high latitude ionosphere, briefly outlined in this yellowy orangey gold box over here, is the region in the upper portion of the Earth, typically spanning from 60 degrees up to the pole in both hemispheres. It contains regions of open and closed magnetic field lines. The open field lines actually allow ions and electrons to escape from the ionosphere via polar wind in the polar cap. That is the uppermost portion of the ionosphere. We go bald up there. The closed magnetic field lines facilitate interhemispheric transport, where things can bounce back and forth between the northern and the southern hemispheres. The auroral oval, the Schwabe line in the middle circle of our Earth there, contains the precipitating energy, electrons, and ions. And so amongst all of these different regions, we have widely changing conditions as the ions are transported to and fro. So one of the interesting and primary transport mechanisms in the high latitude ionospheric region is convection. So the convection is driven by solar wind magnetospheric interactions. If we look at the figure here on the left, we have our sun and solar wind coming in from the left-hand side. It has its own intrinsic magnetic field, which is then interacting with the Earth's magnetic field. These intertanglings of the magnetic field lines connect and then get pulled and draped over the top of our Earth. So if we look at the figure here on the right, at the polar cap, those little circles, 1, 2, 3, 4, 5, and 6, is the motion of these interconnected magnetic field lines. These are beginning to generate the two-cell plasma convection pattern that many of you may have read about in your textbooks. This anti-sunward flow over the polar cap then is connected to a return flow, which is equatorward of the auroral oval. So as the magnetic field lines are pulled, draped over, reconnection in the tail happens, and then they go swoosh back to the beginning to do it all again. So with the return flow, that is the circles 7, 8, and 9 on our right-hand figure here, this flow can actually reach speeds greater than 4 kilometers per second. So it really can zoom along. But that two-cell convection pattern that we're often seeing within the textbooks, it's not always neat and pretty like that. The convection pattern is modulated by different bumps and wiggles in the incoming solar magnetic field. If we look at these two figures here, these are the ionospheric convection patterns as determined by SuperDAR radar observations. So the one on the left, this is from October in 2015. There was a pretty strong IMF, the sun's magnetic field. There was a nice negative BZ. So the direction and orientation of the sun's magnetic field as compared to the Earth's magnetic field are very complementary for creating a lot of energy input coming into the high latitude region. But sometimes they don't quite line up so interestingly, and we have a much smaller convection pattern that's relatively weak, relatively small in latitude spans, and just kind of quiet times. So ultimately, the strength, latitudinal expansion, lumpy blobbiness of the convection patterns is driven by the sun and magnetospheric interactions. And when things are in motion, there will be currents. So looking at that same day, briefly go back. So on the left, that was from October 2015, that same point in time and same latitudinal span, we can also look at the field line currents that are present. So the ampere measurements can be combined to create maps of what the high latitude field line currents are doing. If we are looking at the red interior, can we see mouse? No mouse, okay. So on the left-hand side, we have blue swath and then red swath. That red swath is going to be our region 1 field line currents. They are poleward of the two sets, but the blue swath on the outside on the left, that is our region 2 field line currents. And to be noted, the return currents are red and the downward currents are blue. So when we are connecting with our magnetosphere, currents are coming in from the magnetosphere, they are going downwards in blue, connecting in our ionosphere, and then returning in red. So we get flip-flopped on both sides. So the field line current closure is via the Hall and Pedersen currents, which are dependent upon the local densities. So when they're closing, is it going to be closing 100 kilometers, 110 kilometers, 120 kilometers? It all depends on what the local densities are. And the local densities often are dependent upon what the auroral zone is doing. So this is a video of the aurora as seen from the Themis all-sky imagers. This is also during that October 2015 date. We have a swath of interconnected imagers covering most of Canada and Alaska. Unfortunately, the blue ones are turned off, but you can see within all of the other grayscale circles a wide variety of auroral dynamics occurring. So the auroral precipitation is ionizing the atmosphere, which is increasing the ion densities. Increased ion densities is increasing the local conductivity, which influences how and where those field line currents close. Will it be at 100 kilometers, 120 kilometers? And then the auroral features which are being generated indicate what the magnetosphere is doing. So overall, we have convection, currents, and cool aurora that are all interconnected at high latitudes. Going a little bit deeper into the aurora, I just had to share a couple of images from the International Space Station. I think they're really cool. So we have images from the aurora in the Northern Hemisphere. That's our aurora borealis, but it's also present in the Southern Hemisphere, our aurora australis. And so typically, the Earth's aurora are dominated by excited nitrogen and oxygen. And the reds and greens are caused by the oxygen. And then when you get into little bits of the blues, purples, and pinks, that is from the nitrogen. So depending upon what color we see, we can then begin to determine local compositions. And that goes back to the O/N2 ratios that was discussed previously. And so from the movies on the previous slide, different types of aurora were observed. Two of the common ones, for example, we have our discrete aurora on the left-hand side. This includes a variety of structured forms, such as your arcs, your sheets, your rays. It is generated by field-aligned electric fields far above the ionosphere, accelerating ions that when they do precipitate down at high latitudes, typically have energies from 1 to 10 keV. Now, on the other hand, we also commonly see diffuse aurora. So this is direct precipitation into the lost cone through wave-particle interactions, such as Whistler waves, electron-cyclotron waves, and so forth. This precipitation has energies 10 to 100 keV, and overall there's very little structure. But it should also be noted that aurora is not just an Earth phenomenon. Both of these images here, we have Jupiter on the left and Saturn on the right, are from Hubble, using the ultraviolet capabilities there. At the northern pole of Jupiter here, the aurora is covering an area that is bigger than the Earth and is hundreds of times more energetic. And that little itty bitty dot right there on the right-hand side of all the aurora, that is actually aurora being generated by Io, one of Jupiter's moons, that has all of the volcanoes and it's spitting out all sorts of fun energetic particles. They get trapped in the magnetic field lines, go so whoosh, and we get fun aurora. By comparison, we also have aurora on Saturn. And so this is a mosaic of 3 consecutive days showing that there are enough dynamics within Saturn's aurora that we can see changes in brightness and structure and intensity. And the middle image there of the Saturn's aurora was right after a very large energetic emission from the sun came by. And so a fun thing to note is that on other planets, sometimes the aurora is being generated by other species. Predominantly on Saturn, it is excited by hydrogen. And so if we were to view it in the visible spectrum of light, instead of in the ultraviolet as shown here, the aurora would be viewed more in pink, purple, and red tones. Cassini has some really cool images on that. I suggest you look it up if you are interested. And so then, last but not least, I just wanted to briefly share some of the things that we can do with all of these fun interconnected processes, our convections, our currents, and our cool aurora. This is a modeling case study of the Renew 2 rocket that was launched from Andoya in 2015, I do believe. From that sounding rocket campaign, there was a all-sky imager. That is the panel on the upper left. Over the course of an hour and 15 minutes, it made observations of what the local auroral structure was doing. If we trace along the sounding rocket trajectory, we can build up a kilogram. That is the figure in the bottom right. And so as the aurora comes into screen, brightens, and then over time it's actually propagating northwards. So we get that upward swoop in the brightness within the kilogram on the bottom right. This particular flavor of aurora is called a PMAF, or a poleward moving auroral form. So as the energy is being deposited by the aurora, we have measurements of that, so we can throw that into the model. The sounding rocket campaign also made measurements of what the convection was. There wasn't much, so we just threw a little bit of that into the model as well. And since this is a simulation with 2 knowns, we need to solve for the third one, so it will tell us what the field line currents were doing. So by running the simulation within the model of our incoming precipitation and the convection that was present, the precipitation from the discrete aurora is elevating the electron temperatures. That is the bottom middle panel here. We can see where it gets brighter and the bright sections move around in response to the auroral motions. This increase in electron temperature is resulting in a stronger ambipolar electric field. Well, if the electrons want to go that way, they want to bring the ions with them. And so then that is enhancing the field line upward flow of the plasma. And so that is present in both the upper right panel here, which is showing the ratio of O+ ions to the total density. We can see that big uplifting spike there as ions are driven to a higher altitude. And then also, if we are looking at the middle top panel there, that is our electron density as well. That will show the ionization effects of the incoming precipitation, increasing the local electron density, which is then also being driven upwards. And so the cumulative effect of the incoming auroral precipitation is driving O+ to higher altitudes. If we look at the bottom right panel here, we can see that swoosh, it increases in velocity and then leaves the top of the panel. So that is where we have driven more and more of our ions to higher altitudes. And so all of these interconnected dynamics, the changes in density, the changes in temperature, and the changes in speed are all in response to the incoming auroral precipitation. And as it is changing over space and time, it can be really hypnotic. And then I too have a list of links where I stole all my figures from. Thank you.
Thank you so much, Dr. Boulay, for the interesting talk. It's always so refreshing to see the aurora figures, and it is also one of my most favorites about space physics. Yeah. So our next speaker is Dr. George Clark. Dr. George Clark is a research scientist at Johns Hopkins University Applied Physics Laboratory. He obtained his PhD in physics from the University of Texas at San Antonio in 2014 and spent time at NASA Goddard Space Flight Center. His research interests center on the physics of magnetospheric and auroral plasma phenomena in the magnetospheres of the outer solar system. I'm clearly not a magnetosphere person. He specialized in analyzing and interpreting spacecraft data from missions such as Juno, of which he serves as project scientist for the JEDI instrument, as well as Cassini, JUICE, and Galileo missions. So Dr. George Clark will join us on Zoom. Let's hear from him.
Thank you very much for that introduction. Can you hear me and see me?
Yes, we can.
Would you like me to share my screen?
Yes, please.
Okay, you got it. All right. Yeah, I just would like to apologize for not being there in person. I am home this week, so my wife can travel. So I unfortunately could not make it to San Diego. Oh, can you see everything?
Just 1 second.
Okay.
And I'll let you know once it's.
Okay, sounds good. Maybe I'll just apologize ahead of time if you hear any kids. I asked them to be quiet, but their attention span lasts about 30 seconds. So.
Others are sharing. Maybe we can pull up his. And then I could.
Maybe I'll just talk to the intro slide while you're working on that. I think so. What I'm about to present is just kind of a big picture overview of the various planets in the solar system and their similarities and differences with the magnetospheres and also the auroral systems. Part of the motivation here was there's an effort at GEM right now to do interdisciplinary research, really combining the outer planetary magnetospheres in with what's known really well with Earth's magnetosphere, and so that we can try to understand how things behave in a similar way and also what is different. And so I'm just going to present that here, hopefully generate some excitement, and then offer ways that people can join, and then I'm happy to answer some questions.
Dr. Clark, we can hear you now. Oh,
okay,
we can see your slides.
Oh, great. That's fantastic. Big thank you to the co-authors here of this presentation. So like I was saying, one of the natural questions for me anyways, and for some people that are involved in this focus group panel, is wondering how we can apply all the wonderful physical insight that we have of Earth's coupled magnetosphere, ionosphere, and how that couples to the solar wind, and how we can apply that to the other planets in the solar system. And then maybe interestingly enough, maybe we're able to also learn things and apply that back to the Earth system. So here you can see an example of Earth is well covered from sound and rockets and all sky imagers and dedicated observatories studying magnetospheric and auroral phenomenon, and also solar wind monitors nearby too, allowing you to parameterize the whole system. So as we ask ourselves these questions, we also, ask ourselves naturally, like, why go down this, why embark on this endeavor? And I think Marky Kivelson put it quite well back in 2010, when she gave a comparative talk at GEM, by simply saying we are physicists. And really what that means is that there's a strong desire to understand how well our theories work at the different planets. And so we come up with systems of equations and ideas, and being able to take that to parameter spaces that other space environments give us, we may be able to test how well our idea works, which is great if it does. And then also, very interestingly enough, if it fails, maybe when you consider rotational rates or high magnetic field, strong magnetic fields, and that's also very interesting, and it tells us something that we might be missing. Of course, we've studied one magnetosphere extremely well, and that's the Earth, for reasons I just mentioned. But the Earth can only provides us with a fairly limited parameter space. And so, understanding how rotation rates of planets, what happens when you introduce very different plasma sources, maybe you have active moons in the in the space environment, or maybe wondering how magnetic field changes everything. And so we can go elsewhere too. You know, nearby we have Jupiter, we have Mars, Mercury, all very, very different environments that we can explore. And so really we want to consider these as our natural laboratories to take out these or to carry out these experiments. And the reason why I think we're here today is because we've had dedicated missions in planetary science visiting a lot of these planets. And so the data set, although it's not nearly as mature as around Earth, we're starting to get into a regime now where we can make real comparisons. So just a quick introduction. You know, there's very different types of magnetospheres in the solar system. You have the Earth-like and also the other planets like Jupiter, Saturn, and the ice giants, where you have global dynamos that set up strong magnetic fields that can trap particles and then eventually lead to coupling between the magnetosphere and the ionosphere. You also have other types that look very different, whether it be completely induced like configurations like you'd find at Venus, or maybe kind of like a hybrid at Mars, where you have induced fields, but you also have these highly localized crustal fields that produce, dipole-like configurations. And so how these also interact with the solar wind forcing is of high interest. And of course, not all magnetospheres, even if they have a strongly or global dynamo, are created equal. Here is a plot that shows essentially magnetospheres of the solar system to scale by the planet radius. And so Jupiter is enormous. And then if you look at the other end of the spectrum, you have Mercury, which is quite small. You might be wondering why the vastness of the magnetosphere or its relatively small size matters. And what you find out is things like, travel time, alphane travel time between distant parts of the magnetosphere, and convection times of field lines over the poles can change drastically. And so those time scales might matter depending on the physical phenomena that you're after. And if you go on the other side where Mercury is, you begin to realize that characteristic scales like ion gyro radius and bounce and gyro motions and all like this, stuff like this, actually matter quite a lot. And so that means the more kinetic effects have to be taken into account. Of course, you can also have very different magnetic field configurations. Here are a sample of various planets showing how wonky some of these systems can be. We know Earth pretty well, but then if you look at Uranus and Neptune, you see that their rotational axis and their magnetic moment differ by quite a bit. And so the reason why that is important is because you might have convection and co-rotation in a system no longer necessarily competing with each other. And so you could end up with a fundamentally different solar wind interaction at some of these where you have the magnetic pole rotating drastically as a function of the planet's day. So here's what magnetospheres look like in the solar system with a few characteristics. So you can see the plasma density, the max plasma densities vary quite a bit. Definitely several orders of magnitude depending on the planet that you're interested in. The composition also can vary quite a bit. Earth is primarily hydrogen and oxygen, and I know there's like some O6+2. Sorry, I'm not a terrestrial magnetospheric physicist, so I apologize if some of this information isn't the greatest. But here you can see that, like from Earth, you get primarily solar wind and some contributions from the ionosphere. But then if you look out to the gas giants, where you have active moons embedded deep in their magnetospheres, they actually provide the majority of the material that then gets ionized. And so you can get a lot of water group products. So you can get sulfur, you can get oxygen. And not only do you create these, but you can also create multiply charged versions of those molecules or elements. And so what you end up with is a system that might behave differently depending on the mass and the charge state of the plasma, because those respond to physical processes in those ways. Again, like Earth, that's mostly solar wind driven, meaning you have a Dungy cycle-like convection system. You now move out to maybe gas giants and you see that they're more rotationally driven. So those those freshly created ions deep in the magnetosphere are able to pick up those strong rotational forces from the planet. And then as a result, you have co-rotation driven effects that really kind of expand all the way out to the magnetopause, which is pretty fantastic. And I also want to highlight too that it's not necessarily planets that you just have to look at. There's also a moon, a very interesting moon, Ganymede, in Jupiter's magnetosphere that has its own magnetic field and creates its mini magnetosphere. And that is also a very dynamic environment where they see Dungy cycle convection. So these systems, based on the rotation rates and their plasma sources and all this, might generate large-scale current systems in a very different way than at Earth. So at Earth, you know, this is kind of what the top equation, the perpendicular currents represent. At Earth, you might have region 1, region 2 currents, generally primarily due to gradients in pressure and flow shears at the magnetopause boundary between the solar wind and the Earth's plasma. But as you go out to the gas giants, what you realize is that, you know, pressure gradients, pressure anisotropies and centrifugal forces are dominant. And so you can have a radial current system generated by centrifugal forces that then create this highly extended or stretched field line configuration. And then as you move into the outer magnetospheres, pressure anisotropies, so differences between the parallel and perpendicular components with respect to the local magnetic field, could also play a big role in the configuration of the magnetic field in the dynamics. So you're really able to kind of isolate some of these terms and compare them or look at different dominating factors at different planets. Now, of course, you have to close these currents, and so how that generates acceleration mechanisms and couples to the upper ionosphere is of high interest. So here I'm just going to now outline quickly a few examples of different processes in the outer solar system. So if you look at FAST and you generate a picture of what auroral currents might look like and how they create precipitation, you might look at this left-hand plot, which is of course the FAST observatory that had this low altitude excursions over the Earth's aurora. And you might see periods of upward current right here associated with these mono-energetic electron beams creating more like discrete aurora. Then you have regions of downward current where you don't see a lot of emissions at all. And then you also see hints of some broadband acceleration thought to be driven primarily by alphanic interactions. But if you look at Jupiter and you look at a very similar pass, you know, as the Juno spacecraft, which also has a low altitude excursion of the aurora, and you pass through these auroral arcs, interestingly enough, what you see is you see inverted V's. You see these monodirectional acceleration events or monoenergetic acceleration events. But then what you then learn is that Jupiter, when it demands a lot of current, it seems that it turns or prefers what's called the broadband acceleration mechanism. So we're currently thinking this might be due to Whistler mode waves or perhaps Alfvén waves. But this is a feature that has been statistically significant, meaning that all the time when Jupiter really needs a lot of current, it prefers broadband. So that's fundamentally different than with Earth's MI coupling. Also, here is the plot that shows Jupiter on the top and Earth on the bottom, and it kind of shows these field line configurations for both planets. And on the top and bottom are auroral snapshots. And so although Jupiter is a fast rotator with a different composition and a large magnetosphere, compared to Earth, what you do find is that reconnection events that cause dipolarization and injects plasma in the inner magnetosphere have similar phenomenologies in the auroral emissions. So you can see that they generate between Earth and Jupiter midnight spots, and then the evolution follows to the auroral beads, and then you get these expansion phases, and you can also see these finger-like injection features on the aurora at Jupiter. So it's very interesting that the phenomenology is similar, but how mass and energy are sourced and flow in the systems are very, very different. You can also have differences between diffuse auroral patterns between Earth and Mars, maybe if you look at the diffuse aurora in the very poleward region, this would be like the polar rain type of aurora at Earth. You can see that there's an analog similar to that at Mars, where you see the induced field kind of connected to the solar wind, but it's more global effect driving diffuse aurora kind of at a lot of places in longitude and latitude around the planet. And then you also see that there might be some discrete aurora associated with those crustal magnetic fields. Finally, you can get intense ion outflow associated with the moons. And the previous speaker was kind of hinting or definitely showed a picture of Io generating a lot of emission. And so here is a plot or a graphic rather that illustrates how you can get intense ion outflow associated with the alphanic interaction between Io and Jupiter. So you have low energy ions sourced near Io itself, and then you create these kind of disturbances in the flow that set up these alphane wave packets. Those plasma waves can then basically cascade and fluctuate, and how they couple to the ionosphere, which is still kind of a big question. But we do know that they provide a lot of electron precipitation into the upper atmosphere at Jupiter. But then that can further manifest into generation of EMIC waves and upwelling. And what you get is ion outflows with energies well into the hundreds of keV along the whole tail, which is very interesting. So this is a energetic plasma source at Jupiter. Here is a plot highlighting the different polar caps between Jupiter, Earth, and Saturn. And I'll kind of be quick here. I think we're running out of time. The takeaway here is that unlike Jupiter, where you have Earth and Saturn and you have this oval, auroral oval that might define the open closed field line boundaries, you look at Jupiter and you see that there are lots of emissions in what you might believe is open flux connected to the solar wind. And you also see that there's X-ray generation in there too. And so what you learn right away by looking at this is that not all polar caps are the same, and that you can have lots of emissions and interesting acceleration regions embedded in this polar cap. And what we found through magnetic field modeling is that the polar cap is likely a closed field region with just small crescents of open field connected to the solar wind. So this is a simulation, and you can see that these closed field lines represented by black can go out to several hundred RJ in the tail. And the green here illustrating the open flux is constrained to the small crescent just poleward of the main oval aurora that I showed earlier. So that was my very quick talk on some of the comparative aspects with other planets. It boils down to that we're gifted with a really diverse set of planetary environments, making it possible to kind of probe this parameter regime in a systematic way to learn how our theories operate and if they are similar or different and why. And we also can leverage the fact that some planets make it easier for us to understand processes at Earth, perhaps because there's not competing processes masking the physics. And I just want to say that workshop style meetings like GEM and CEDAR that facilitate these kind of collaborative aspects is really key for us making good progress, hopefully in the next several years to come. And please, if you're interested, reach out and stay tuned with our GEM focus group. So that's it.
Thank you, Dr. Clark. Very
welcome.
interesting presentation. Thank you. We have a lot of information about those outer solar system planets I was not aware of. Okay.
Now, I can't hear the audience. I don't know if you allow questions, but if there are any questions, I'd be happy to answer them now or follow up through email.
So we'll have a Q&A in hopefully about 45 minutes, and we will direct our questions to you at that time, if that's all right.
Understood. Yep. Great. Thank you.
Thank you, sir. Okay, so next on the agenda, we have Dr. Nicholas Petitella. Dr. Petitella is a research scientist at the National Center for Atmospheric Research, High Altitude Observatory. He received his PhD from the University of Colorado in 2011 and was an ASP postdoctoral fellow at NCAR HAO from 2011 to 2013. Following his time as a postdoctoral fellow, he joined the UCAR Cosmic Program Office as a project scientist. He returned to the HAO in 2016 as a scientist in the Atmosphere, Ionosphere, and Meteosphere Department. His primary research interest is understanding the influence of lower atmospheric waves on the spatial and temporal variability of the upper atmosphere. Yes.
Yeah, it's not. Yes, sorry. Okay. So yeah, thanks for introduction, and I'll give a brief overview in 15 minutes on data assimilation, focusing mostly on the CEDAR science. So just brief outline of what I'll discuss here. First, just a simple overview of what is data assimilation for those who are not familiar with it. Then why we would want to use data assimilation for either science or for operational type applications. Then I'll give some examples, and then I'll conclude with some of the sort of outstanding challenges in using data assimilation for CEDAR type of science. So first, just what is data assimilation? So as a very simple depiction of it is shown here. And really what we want to do with data assimilation is statistically combine a background model with observations to get a better estimate of our current state. So we know that the model is not perfect and observations are sort of limited. So by combining the two, we should be able to leverage advantage of both. So here is just a simple example. In the black here, we have, say, the true atmosphere or ionosphere that has some trajectory in going forward in time. And then the red dots here are the observation points, which are not quite the same as the truth, right? Because observation has some error associated with it. And then the orange here is our model that we would be projecting forward in time. And you can see the model, of course, doesn't perfectly agree with the real atmosphere. So it has some error. And with data assimilation, we want to get this sort of blue line, which is what our estimate of the best state is, which initially would follow the model trajectory. And then when we hit the time of the observation and we're doing the assimilation, we have this correction to the model state based on they will bring it closer to observation. And we would call this an analysis step typically. And then we run the model again forward in time, apply another correction. And over time, hopefully we want to get closer and closer to the true state, but still use our model to sort of project forward in time and give us potentially more information than we get from the observation alone. So this is a sort of simple depiction. In equation form, you can write it like this, where we have some state vector, which is a forecast state of the model, which in a geophysical model like ionosphere or thermosphere, this is going to be many, could be on the order of thousands of dimension, depending on the size of your model. Then we add to that some weight matrix, and then here we have y here is an observation vector, and then h converts the model state to the observation space, and then this is essentially the difference between observation and model state, and then we add that to our forecast state to get some analysis state. And this weight or gain matrix, as it is sometimes called, is often written in this form here, where we have a background error matrix based on the model, and then also an observation error matrix. And a few things to consider here is, one, this error matrix is actually quite important for the observation. So for people who focus more on observation, really understanding the error in your observation is a crucial thing for data assimilation to work, because if you over or under specify the error, it ends up impacting how well you can effectively use that observation. So really having realistic error estimation from observation is crucial. And then also understanding the background error in the model is also important. So for data assimilation to work effectively, you need to really understand the error sources. And one thing to consider with ionosphere-thermosphere especially is the sort of state of the system and how that comes into play. So there's, generally speaking, you can think of as two types of dynamical system. One would be a chaotic system and one would be strongly forced. So chaotic system essentially means that if you have a different in the initial condition of the system and then propagate it forward in time, a small difference will lead to a drastic difference in the state. This is a sort of so-called butterfly effect, where you have some small perturbation in initial condition, and then that leads to a sort of drastically different state in the future. And the alternative is what we would call strongly forced, where independent of the initial condition, because you're applying the same external forcing over time, it's going to sort of converge to the same state in the future. And you can sort of somewhat classify conditions on some spectrum between these two. Numerical weather prediction, which is a sort of classical application of data assimilation that we're all familiar with for tropospheric weather prediction, is much more of a chaotic system where it's initial condition dependent. Ionosphere-thermosphere is sort of trending towards a forced system, but it's not fully forced. Initial condition still matter. And then magnetosphere is probably a bit more towards the strongly forced side. But what this means is that, though there is a lot of research in data assimilation that has been done for numerical weather prediction, because the system is slightly different for ionosphere-thermosphere, you cannot just, blindly apply what has been done there and apply it to, ionosphere-thermosphere. So it requires sort of new technique for data assimilation to some extent. And because of this, there's a sort of contrasting ways of doing data assimilation. One would be to estimate the state, which is what you would do for a chaotic system, or you can estimate the driver, which would be a strongly forced system. So there's a bit of different approaches being taken for data assimilation in upper atmosphere. And so what are some of benefits for doing data assimilation? I've discussed some of these, but really, we all know that observation are limited in the scope, right? This is both in like spatial and temporal sampling. We can't do everywhere, but also, right, what you can and cannot observe is another factor to consider, right? There's a lot of things we want to know about the upper atmosphere, but we can't observe it because it's just too difficult to observe. So, that has some limitations. And we also know that, numerical simulations are always going to have some uncertainty associated with them. There's always assumptions, parameterizations that are unknown, and so they're not going to be perfect. So really, we want to use data assimilation. We can leverage these two together to get a better, global picture by constraining the model with the observation information that we have, and that should, provide some, greater than the sum of the two parts. And here are some example applications of what you can use data assimilation for. One is just you get a better estimate of the atmospheric state. And so you can use this for process studies of middle and upper atmosphere, right? Rather than just using an unconstrained numerical simulation. If you're constraining it with observation, it should give you a better representation of the atmosphere. One, it can give you, in a sense of where you have large model errors in your, right? If you look at where the observation increments are large in the model, that tells you where your model is performing poorly. So where this sort of observation minus model difference is large and you're giving big adjustments, that's where you might want to focus model improvement. You can use data assimilation to estimate uncertain model parameters or forcing. That is another area. So again, to improve the model. And another area is, using it to get initial conditions that you can then use for investigating predictability, either in an operational sense or from a scientific sense of just understanding what is predictability of the upper atmosphere. And now I'll just give a few examples of where data assimilation has proven useful and what it can do. So this is example of a sudden stratospheric warming event. This is altitude on the y-axis, and then the x-axis is time. And this is the polar cap temperature. So we're focusing here on kind of middle atmosphere. And the top left panel here is if we just constrain the model up to about 50 kilometers, somewhere around this height here. And then this bottom left panel is when we use data assimilation to constrain it to a higher altitude by using middle atmosphere observations. And then here on the upper right are the observations themselves. And the key point here I want you to see is this sort of what we call an elevated stratopause that occurs here, where it decays very strongly in this case, but maintains a much higher altitude when we do the data assimilation, which is more consistent with the observation. So we're getting better representation of middle atmosphere dynamics by ingesting the observations into the model. And this is temperature, but this then has other impacts on, say, composition and transport of middle atmosphere. Here again is the same type of depiction, where this is where we just constrain to lower altitude. Then here is where we ingest higher altitude data. And this is nitric oxide transport downward into a stratosphere. You can see this sort of tongue of enhanced nitric oxide goes to lower altitude, in this case, where we do the data assimilation, which is more consistent with what is seen in the observation. So by getting better representation of dynamics, it then has subsequent effect on the chemistry of atmosphere as well. And here is another example focusing on middle atmosphere, where if we have on the left here, this is from the Navy data assimilation system. The left plot here is constraining again to a higher altitude with data assimilation. On the right is without. And this is a tidal amplitude of one of these tides that Scott talked about, that's driven by troposphere convection, but then propagates upward and impacts ionosphere-thermosphere. You can see the difference in the tidal amplitude is about the doubling. So by constraining the model, you're really getting a huge difference in the state. So data assimilation is really kind of crucial to get these dynamics correct. And one other aspect where data assimilation can really improve our understanding is by using the observations that we do have to constrain unobserved states of the atmosphere. So, right, we can only observe certain things, and some things are easier to observe than others, but we can use that information to then constrain other states of the model through covariance information. Here is just, cartoon example where, say, we have an observation of the total electron content, which is very, relatively easy observation to make from the ground. And then we have the model state, which could be temperature, which is a bit harder to observe. And if these are correlated in some way, then if we say adjust the total electron content by a certain amount in the model, then we know we can also adjust the temperature by the corresponding amount. And then this can really make use of observations that are easier to observe to then leverage them for other aspects. And here is an example. This is a sort of numerical experiment where we know the truth in the model, which is here. This is temperature, longitude versus latitude in the thermosphere. Here is the truth. Here is the model run that we did without any ionosphere data assimilation. Here is ionosphere assimilation where we just adjust the ionosphere state. And here in the bottom right is assimilating ionosphere observations, but also adjusting the thermospheric composition and temperature. And though it's not perfect because it depends a bit on where we have observation, you can see the bias in the thermospheric temperature. In this case, just from assimilating ionosphere data, can then get better agreement with what we know as the truth. So by assimilating ionosphere data, we can in turn improve thermosphere temperature and also things like neutral density for satellite drag. Here's just another example, again, where we knew the truth. This is vertical plasma drift in the ionosphere at the equator. This is day of the month, and then this is local time. Here's the known truth. Here is a case where we are assimilating the ICON neutral wind observations, and this is the error. And then here is the case where we don't assimilate the ICON neutral wind data. So if you just look at, say, that in the daytime, here, these errors are significantly lower than we have in this case here. So by assimilating neutral wind data from ICON, we could reduce the error in, say, vertical plasma drift because of the connection between these two parameters. And here is another example where we look at irregularity formation. On the left here is observed irregularities from ground-based GPS data. And here was a storm that occurred, and there was observed case showed a lot of irregularities in India and not many in Taiwan in this case. And if you look here on the right, the dashed line is if you don't do any data assimilation in the model and then calculate the growth rate of irregularities. And in that, the dash case, you can see it predict in the model large irregularities over Taiwan and not many over India, so stronger irregularities. But this is opposite of what was seen in observation. But when observation are assimilated into the model, then you see a much stronger growth rate over the Indian sector and lower over Taiwan, consistent with observation. So this, by constraining the model, you're getting a much better representation of what actually happened, whereas the model is incorrect. And this is sort of growth rate of irregularities, and you get that by just assimilating sort of TEC data itself. And one last example I'll show, this is looking at kind of forcing estimation instead of state estimation that I mentioned earlier. So here on the upper left is these are comparisons of neutral density against the GRACE satellite, looking at accelerometer data in blue, and then the sort of yellowish line here is the model simulation without any data assimilation. And you can see there are errors in the neutral density, and that then impacts, of course, satellite drag and orbit prediction. So these errors are quite important. And then in the bottom here is when observations from a different satellite were used to correct the forcing of the model in terms of the solar flux and geomagnetic forcing. And then here you can see in orange, the resulting thermosphere mass density is in much better agreement with the observation. And these are sort of independent observation. And here on the upper right is what the estimate of the forcing was. So for F10.7, the observed is in the blue, and then the orange is the estimation. And you can see it generally tracks, but there's some slight differences. And so this is sort of correcting the forcing into the model is being done to get a much better agreement with the mass density. And so just as to conclude, I'll discuss a few of sort of remaining, I think, a challenge for data assimilation, focusing on middle and upper atmosphere. One thing, there's different approaches, as I said, is either state estimation or driver estimation. And I think understanding really the advantage and disadvantage of these two approaches and how they can be applied for different science or operational goals remains unclear. We generally speaking, have a very sparsely observed system in the middle and upper atmosphere compared to, say, the troposphere, and how to really make the most effective use of these data and is a crucial area, right? Because if you more effectively can use this data, then it becomes more powerful in the data assimilation, whereas using it ineffectively, you're kind of not leveraging it to the full extent possible. Lot of our data assimilation methods rely on ensemble common filter, and methods for generating the ensemble spread is actually quite difficult because it is, this partly forced system. So this is I think, active area of research. And then one thing I didn't go into here, but most of our data assimilation methods in the ionosphere-thermosphere domain are kind of primitive, I would say, techniques where we use kind of ensemble common filter or some basic data assimilation. Whereas numerical weather prediction, they have much more advanced techniques for doing data assimilation, like 4D VAR or hybrid cases where you use both variational and ensemble approaches together. And these have never really been developed and tested for upper atmosphere. So really, advancing these data assimilation techniques for our science, I think, would help advance things significantly. So I will conclude there, and thank you for your attention.
Thank you so much, Dr. Patella, for the great talk. I think leveraging the tools and equipments we have, it really brings us the great opportunity for the current generation, as well as the future scientists sitting in this room. So our next speaker is Dr. Duncan Ostark. Dr. Ostark is a research assistant professor at the Geophysical Institute of University of Alaska at Fairbanks. She received her PhD in space science and scientific computing from the University of Michigan in 2018 and served as a postdoctoral scholar at both NASA JPL and UAF. Her research interests include understanding the physical process related to Earth's magnetosphere, ionosphere, and thermosphere across different spatial temporal scales. She's also a co-PI of the dynamics and impacts of electrons and ions in the Earth's magnetosphere ionosphere system, a NSF answers proposal, which was recently funded. So without further ado, let's hear about Dr. Ostark about the machine learning.
Inquisition. While we are waiting, maybe I can start. I wanted to ask how many of you incorporate elements of machine learning in your research? Can you show hands and a little higher because I can see? Oh, it's a good classification problem, more on this side of the room rather than that. Perfect. So I guess we are ready. Thank you so much. Thank you. Thank you so much, Andrew. Yes, thank you, Andrew and Zishan, for also inviting me. So I want to start with, now let's see, technical difficulties don't end. So machine learning, again, is something that we talk about a lot recently, and it has a really high entry level in the previous like 1990s and 2000s. But with most open data packages and software, now it's really easy to teach yourself machine learning. And it helps to keep in mind that what it basically aims to do is to understand information. So let's say we have an electron density profile like this, because this is CEDAR. What would be the first thing you would try to infer from this data? And I'm wondering what if the students would like to say what they might be seeing here. What information does this hand-drawn graph represent to you? Any takers? I teach this class. I'm used to awkward silences, so I'll wait, but we have 15 minutes. So I would maybe say, like, there's a trend, right, that we can see that basically this whole data has a slope that shows the data is increasing. The other information you can get out of this is there's a pattern. We see these oscillations at certain frequencies. You can see that this could be also deduced from the information of this electron density profile that we are seeing. And lastly, there's an irregularity. So this is basically gives us a framework how to apply machine learning algorithms and to understand or extract which type of information we want out of a simple data set. If you are, for example, using machine learning for data calibration, excluding the trend will help you to get a better data. If you want to understand the pattern, the frequencies, whether there are certain drivers of a system, then you would want to find the pattern. And anomaly detection would be very helpful, for example, in finding where the irregularities occur in your data set. You can think of this as maybe a temperature data. If we have a particularly hot day or a cold day, that might constitute an irregularity. If you have, for example, diurnal variations, that would be your pattern. And the rising temperatures, for example, due to the climate change could be the trend as well that you see. So it really builds upon some of the statistical techniques that we have been applying for a long time. You can see that talking about learning, especially for machine, we look at 3 distinct categories, which also overlap at times. The first one is the supervised learning, and this is our regular regression classification techniques where we are supervising the machine. We are providing sample data set where the machine learns from. The other one is unsupervised learning. This is something we use again for anomaly detection, clustering, dimensionality reduction, which is something that is going to be talked a lot in the next week as well. For example, principal component analysis, empirical orthogonal functions, they all go into the dimensionality reduction techniques. So this helps us simplify our system and capture the most important components. And lastly, we have the reinforcement learning, which is something that we widely see used in industry and applications like ChatGPT, which is used in decision-making and optimization because it can have a reward type of system that help the machine pick the best outcomes. So today I want to focus on the supervised learning because of the time limits that we have, but we start with the basic regression analysis. So it is the most helpful technique for us to understand the immediate relationship between an independent variable and dependent variables. So you have been probably doing this since middle school. We have one variable X and how it can help us determine the values of Y constitutes a regression problem. So for regression, we can look at different categories like linear regression, polynomial regression, and logistic regression, which all have their uses. So for example, if we were to look at the trend, you can see we would use linear regression, polynomial regression if you want to subtract that pattern data. There are more sophisticated ways these days to use these polynomial regression techniques because you can see that the order would also affect the quality of our fitting. What we can do with regression, again, that is very helpful, is to interpolate or extrapolate. So interpolation could help us fill data gaps, and extrapolation helps us predict or forecast immediate future. Looking at linear regression, you can see it's basically a slope function. We have the data in Y, and we are trying to fit the X values with the weights, basically, to this equation. Polynomial regression is a little bit more complex than the linear regression, right? So we start adding higher order parameters now in polynomial regression, and more polynomial terms can be added to capture the variability of the system in addition to the linear regression problem. But one problem with the polynomial regression is you will end up having, and the mouse is here now, you will end up having these or really high orders, oscillations, and really parabola-like structures. This is where regularized regression comes in. So you may have heard of lasso regression, ridge regression, or elastic net, which combines them both, which attributes different weights to the functions that you see here. So these weights can help us regularize the functions a little bit better and have a better fitting for higher order polynomials. The way that we evaluate regression is through calculating error. And you can see here our regression curve between actual values and predicted values. And you can see this green dashed line basically shows where they match perfectly. So the error would be the distance of our prediction to this green line. And we can calculate it in different manners. One of them is mean absolute error, which is analogous to the L1 norm. We have mean absolute percentage error, which gives us a better understanding in means of percentages. We have mean squared error, the L2 norm, and the root mean square error, the L2 norm, which helps us all assess the performance of our fit. Another mostly used supervised learning technique is classification, like we did in the first example, right? How many people use machine learning versus how many people don't use machine learning. I would say just maybe down the middle line would be a good way to classify this problem. So it helps us predict classes and categories in the future. So this is something you can use, for example, again, anomaly detection, right? So that data line that we looked in the beginning had one anomaly, and maybe continuity of the data or the values that it might have being too high or too low can help us classify these type of signatures. So a classification application consists of a classifier. This is an algorithm you may choose, which we are going to discuss next. A model that helps predict the class, features that help us define things like the questions we ask to a group of points that you see here, like how green are you, or are you more blue? And the binary classification, it's a task with two outcomes. A multi-class classification is each sample belongs to only one class. Multi-label classification, which is where one point could belong to two different classes, and the target, which is the label that we attribute to that point that we are trying to predict. And lastly, we will look at how this classification is evaluated. So the first one is binary classification. This is a case where you have either or situation. And so we have learned that the from binary classification that if and else statements could be very helpful. So for example, these days, if an unknown number calls you, your phone will have a label that says potential spam, right? So this is a good example of binary classification. Basically, what the phone does is the number known? Is it in your contact lists or not? If yes, it is a safe call. If not, it can be a potential spam. So in cases that are a little bit more complicated, you know, as binary is by itself a very biased classification, we can use logarithmic classification. So using logistic regression, we can attribute different probabilities that can help us define a class. So here, for example, you can see if we applied logarithmic regression to our previous problem to classify it, we can see that there's a highly likely probability that it's a potential spam, or depending on the threshold you apply, it could be a safe call. A more complicated version of this is the decision trees. So, for example, we start again with the same premise, whether the phone number is known. If yes, it's safe. If not, we can talk, for example, it might be a situation where the first 3 digits could be your area code, which is more likely to deceive you because you can think that it's maybe calling you back about an appointment. And when you pick it up, then you hear the other side asking whether that this call was about your car's extended warranty. And you're like, okay, this is potentially spam. And if it's no, they can also claim to be calling you from IRS. There can be an automated sound in the end of the line. So all these help us, you know, define the feature set that we talked about. These are our independent parameters, different questions we ask to the system to determine whether it is a potentially spam or not. So this is how a decision tree structure looks like. We start with the root node, right? So this could be randomized, and then we go into decisions in our system where, again, we make decisions based on the questions we ask. And from here, we can go to further down the branches of the decision tree and make determinations. And here you can see how each different node or leaf is determined. And these are all parameters you can further fine tune to get higher performance from your model. So decision trees are known to overfit. They can both be used for regression or classification because you can have a discrete function and you can apply it as discrete function as a decision tree problem for regression. But if left unpruned or if we do not do anything about these hyperparameters, like how many leaves do we have, how many decisions we want, how many children on left, how many children on right, this terminology is getting crazy. But you can see that it could be quickly go out of hand and overfit. That is why we use ensemble methods like random forest, which helps us overcome overfitting, because we can then change the randomization and take the average for regression or the most frequently selected parameter for classification problems. Again, I included the scikit-learn packages in Python. That is really helpful. These are just objects, and you can use them as functions immediately to your predicted and actual values later. Here you can see how we apply random forest models like these ensemble models for data gap prediction, for example, in solar wind. If you're working with geomagnetic storms, you probably have the situation where Omni data will have some data gaps, right? So here, one of my previous students, Jasmine Kobayashi, was applying an ensemble random forest model to fit the this is a test case, but to show how basic the performance varies compared to a linear interpolation. And lastly, the one final method I want to talk about today is the K nearest neighbor. This K is the value of how many points, neighboring points, you want to include in the system. Here you can see in this cluster, for example, we can include a K equals to 5, and black dot is the that we want to predict. So what this K neighbor model would do then is to count how the points that we defined, that 5 points in its closest vicinity, and attribute what that color, what that black dot would be based on the majority of choices. The way that we evaluate this is through the confusion matrix. So especially it is a bit confusing in the beginning because of the false negatives, but here it's breaking down into different labels. True positive is when we predict 1 and the actual class is 1. A false positive is when we predict 1, but it was actually a point that belongs to another class. A true negative is when we predict it to be for the other label, which is verified with the actual values we have. And a false negative is we predict an event when there is no event. This all depends on the threshold we apply. We talked about in logarithmic regression and classification. The threshold is generally 0.5. So if we don't have a class that is equally distributed, for example, unevenly distributed classes could be for most of the nights are clear skies, right? And we can have discrete aurora like Megan was talking about very rarely, like in this case. So if we apply a prediction threshold that is 0.1, you will see that this will create a confusion matrix where most of the cases are not predicted when there is aurora. So we can also lower the threshold to improve our model performance, as you can see here, now that most of the points that are indicating a discrete aurora would be captured with a method like this. So changing the thresholds and looking at how this true positive and false negatives change is a way to understand and evaluate how the classification algorithms work. I'm not going to talk too much about this, but precision recall techniques and the receiver operating characteristic curves basically aims to try to do just that and understand how well classification works. So for example, we can have this classification application for predicting different classes of aurora. This is a study conducted by Clausen and Nikish, and you can see that they have different labels for different images, and they can apply something as simple as rich classifier to achieve very high accuracy. Lastly, I want to just briefly mention that evaluating the accuracy of models is also very important, not only their performance, but their accuracy. We want to avoid learning the noise. So here you can see a well representation of this for regression. Okay, here we have mouse again. For regression, classification, and some deep learning that we didn't talk about. But when we overfit a problem, you can see that it tries to learn what the all behavior of the all points, which is very troublesome for noisy data, and it does inhibit the ability of a model to generalize a solution. So here are some suggestions for dealing with underfitting and overfitting. What we want is a model that doesn't always perform perfectly, but performs relatively well, as you can see in this middle column. So with that, I want to end by showing you some resources for ethical machine learning framework. This is something we talk about a lot, but today we touched upon supervised learning, but the more complicated the models get, the more of a black box it gets. And there are certain implications of this because of the bias that it introduces. So here are basically this GitHub link will take you to most of these documents. And thank you.
Thank you, Dr. Oster. Really interested to see how developing the models for detecting auroras is going to grow in the coming years. Okay, so just a couple quick announcements, guys. We're going to change the Q&A to be 10 minutes long because we're running a little bit behind schedule. We're still going to go with Slido and do the top rated questions to the speakers, but just so you guys all know. Okay, so our next speaker is going to be Dr. Ed Thyman. Dr. Thyman is a research scientist at the University of Colorado's Laboratory for Atmospheric and Space Physics, focusing on extreme ultraviolet instrumentation. After receiving his PhD in electrical engineering from University of Colorado in 2016, which focused on solar flares, he began using EUV solar irradiance to probe planetary upper atmospheres via solar occultations, resulting in new measurements of the upper atmosphere of Earth and Mars. He's actively involved in multiple NASA missions, including being the PI of the occultation wave limb sounder, the deputy PI of the Maven EUV monitor, and instrument scientist for the total irradiance monitor as well. Thank you. Okay.
All right. So I guess I'll start with the disclaimer that I kind of made everything in my talk up, and by that I mean if you have 10 different PIs up here, you're going to get 10 different talks because they're all based on our own experiences and the folks we know. So my threshold was not to include any wrong information or give any bad advice, and I think I at least did that. So show of hands, how many of you are graduate students at the graduate level? Okay, and how many are undergraduate students? Okay, and first year postdocs? Okay, so I think you can take what you will out of this talk. I don't think it really matters at your what your career level is. When I really decided to be a PI, I was actually had finished my master's and was working as an engineer in an academic lab. At that point, decided I wanted to go back. So I guess I'd say it's probably never too late. Let's see, how do I advance this thing? No. The trackpad? Oh, I got you. Okay. Okay, so a little bit about me. Well, there was my introduction. So that was already given. Scientific interests are in planetary upper atmosphere, solar corona, and solar flares and space weather. On a personal note, I'm a first generation college grad, Air Force vet, and was a non-traditional undergrad. And I'm happy to share my experience and listen to yours. Just reach out, and there's my email. So what's a PI anyway? So a hardware principal investigator or PI is the senior leader of a hardware program, ultimately responsible for the program's success or failure and the day-to-day operations and budget. Typically, one person can't manage all that as well as the science. So a PI would be partnered with a program manager that may make most of the day-to-day decisions. So in summary, the PI must lead the team and be knowledgeable of both the hardware and science. Here's the org chart for OWL. So NASA is, in charge of the whole program. So we report to NASA. And then under that sits the PI and the deputy PI. And then, there's two parallel paths. The science co-Is report to the PI, but then the instrument program is there on the right, and that goes through a program manager who usually oversees most of the day-to-day operations of the instrument development, and then once on orbit, the flight operations. So instrument versus mission PI. An instrument PI is typically the lead technical expert of a spacecraft, instrument, or experiment, and responsible for its development and operation. Instrument PIs are often experimentalists and hardware-oriented. This isn't always the case. There are some instruments that have an instrument PI that's really the science leader, and there was early on an instrument scientist who was responsible for the development. And then instrument PIs may also lead small CubeSat missions because the whole purpose of CubeSats is to develop new instrument technology. When I think of a mission PI, usually I think of bigger missions, planetary missions or big Explorer class missions, and those PIs typically lead a collection of instruments on a spacecraft and are responsible for the overall program. Not all missions are PI led. The mission PI is responsible for both the instruments, the spacecraft, and the science team. And then the mission team is comprised of instrumenters, modelers, and science data analysts. Sometimes people move from left to right. They start out as an instrument PI and become mission PIs, but I think in a number of cases, people just go directly from doing what they're doing to being a mission PI without having any specific hardware experience. So I'm going to give a couple examples of an instrument PI and a mission PI. I'll start with Arthur Walker Jr., really a personal hero of mine and a pioneer in my field of solar EUV optics. He developed the first XUV normal incidence telescope. This is the same technology that's used in modern EUV imagery of the sun by AIA and SUVI. So anytime you see a picture of of the solar corona that is just fascinating, you can thank Dr. Walker Jr. After completing his PhD, he joined the Air Force and developed rocket instruments to measure the Van Allen belts. He then went to Stanford, and this was I think his key insight is he partnered with somebody outside of the field, somebody from the material science faculty, to apply their technology to astrophysical optics. He led multiple rocket payloads in the 80s and 90s, measured the first full disk image of the solar corona that made the cover of Science in 1988, I think, and then later developed rockets developed technology that were used on the Chandra X-ray telescope. He was Sally Ride's PhD advisor. And then, sadly, I think he died far too early. I think there was still a lot more that he could have done. And then the next PI example I want to give is a mission PI. This is Dr. Shannon Curry. She's actually, full disclosure, my boss on Maven. She's the PI of the Maven mission orbiting Mars. She completed her BS and then worked as a systems engineer at Lockheed Martin before going on and getting her PhD. After her PhD, she joined Berkeley as a postdoc on the Maven program. She really established herself as an early career expert of Maven science, specializing in atmospheric evolution and the solar wind interaction with the Mars environment. She authored and co-authored 68 papers. And then in 2021, she was selected as the Maven PI to replace the retiring PI. So she really didn't have any, hardware experience per se, but she was still able to make that leap to becoming a mission PI. She's guest investigator on Parker Solar Probe and project scientist on, this is the older set of slides, that should be project scientist on Escapade. But that kind of, brings me into my next slide, which is, instrument and mission life cycles are long, so PIs rarely work on a single program. And so this is just kind of a rough day in the life of things a PI might encounter, maybe 1 to 4 hours of instrument and mission meetings. This is really meeting with the team to make sure everything is going as expected or as planned. So that could be spacecraft operation status, science planning, looking at instrument health and safety, instrument development, and engineering meetings. It could be an hour of administrative or budgetary work, 1 to 2 hours of email correspondence. I think we all deal with that no matter what we're doing. 1 to 3 hours of laboratory payload development work, a couple hours of instrument calibration, a few hours of data analysis and paper presentation and writing, and then time allotted to develop the next proposal. And so of course you can't do all of this in one day, but this is just sort of an example of the things that that a PI is managing throughout the week. So I was actually going to skip this because I'm long on time. I'm just going to be short on time, so I could go back to that, but okay, so a little bit on instrument PI education. So I would, if you still have the chance, I would say take substantial engineering coursework. It's going to aid in the understanding of the technical details of an instrument. So non-engineering majors should, if they can, take engineering electives. I would say most instruments do a lot more electrical engineering than aerospace engineering. So in so many cases, if you had to choose, I think having some electronics background would be helpful. And then you need to, find a hardware mentor, and whether that's if you're at the undergraduate level or the graduate level or at the postdoc level, you really need to have a hardware mentor. There's certain schools that have big hardware programs, but don't just look at those if you are, looking to move, because there's many smaller programs out there. Many universities, maybe have 1 or 2 people working on a rocket program. So there's opportunities across the country. On that note, rockets are great teaching programs. There's lower risk, there's less QA, there's more student involvement, and there's maybe more likelihood of actually getting real data than you would on a CubeSat, which is much higher risk. And then there's the NASA mission design schools. If you're not aware, there's one for planetary science, heliophysics, and astrophysics. So you should consider applying to those, because their whole intent is to train the next generation of PIs. Instrument PI good practices: become an expert in the science. The hardware is often a massive time sink, but it is fun to work on. But if you want to be a PI or an instrument scientist rather than an engineer, you really need to understand the science of the measurement target. You should always look for open questions. Always look for opportunities to apply your specialty within and outside your field of interest, and collaborate and network. Get to know others in your field with specialties that could enhance your investigation. If you have a need on a proposal, don't hesitate to cold call somebody that you know of that you've never met. People love to be invited on proposals, so that's should be an easy thing to do. Okay, so getting your first investigation, you need to start with a question. And so, my recommendation is find a clear and solvable science question. Proposals get rejected all the time because they can't show a science question can be closed. But in my opinion, this should never happen. You get to choose the science question. So pick a question that you can show that can be closed. And to that end, you should have a section in your proposal that says path to closure and lays it out for the review panel. This is how we're going to close this question. Addressing an open scientific controversy is an easy way to convince a panel your investigation is compelling. So if there's a debate in the community that could use one particular measurement, see if you can make that measurement and then explain that controversy in your proposal. Because most of the time, the people who are reviewing your proposal are not going to be experts in the field. So if they have some evidence that you're answering something that isn't known and people are arguing about, it's helpful. Write a clear science traceability matrix, or STM. The STM traces the science questions to the measurement. And I would suggest, use the template that's given in the proposal. Every proposal AO, every AO is going to give you an example STM, and it's probably better to use that than invent your own, just to make it easier on the review panel. And so for those who haven't seen an STM, here is an example. This is the one that we had on OWLS. Basically, it traces the science questions to the measurements. And in this case, it goes through an objective, but it traces each science question to an instrument that can help answer that question. And then it talks about what that instrument has to measure and what the projected performance is of that measurement. Okay, so the other thing you need to do to get your first investigation is find the right AO. So I do more heliophysics, so these are heliophysics recommendations. There's the HFOS program that funds concepts. So this is typically around $100K for 1 year, but it's enough to really get the meat of a future hardware proposal. And flesh out some things that really just are at the conceptual stage. There's the HTIDE's ITD program, which funds instrument tech development. This is typically about $1 million for 3 years. Then there's LCAS, which funds balloons and rockets, as well as instruments to develop for balloons and rockets. HFORT is the heliophysics CubeSat and hosted payload program. And then these are all training grounds for larger Explorer class PI-led missions. So you can, continue to go up the chain. I would also say that, planetary science overlaps with CEDAR science. If you're interested in gravity waves at Earth, there's a lot of gravity waves at Mars. And there are planetary science programs that could develop that instrumentation like Picasso and Matisse. And then, learn from your rejected proposals, fix the weaknesses, get clarity from the program officer and repropose again and again. A selected proposal often is not proposed just once, but, if it really is a bad idea, if there's something wrong with it, you should be flexible enough to move on. And then, really short on a path to a mission PI, and I maybe you got this from the 2 examples that I gave. I think there's a much more clear path to becoming an instrument PI. Becoming a mission PI is a bit more nebulous, and it may take a career to realize. You should be an expert in your field and in analyzing measurements and observations. You don't have to be hardware oriented, but you need to have contacts. You need to have a network of people that you could call on to collaborate with to build a mission. And then you need to be a good program manager and leader. And then I guess just real quick on my own path, I enlisted in the Air Force out of high school. Didn't really know what I wanted to do and needed money for college. I then got my BS in engineering physics. Went directly to grad school, got my MS in physics, but then I quit school and went on to work as an engineer for a few years. Returned to get my PhD, finally in electrical engineering. My PhD focused on solar EUV irradiance models, but then in my postdoc work, I started applying that knowledge to doing solar occultations, and then use that expertise to propose the OWLS mission to measure gravity wave effects on the thermosphere via solar occultations. And it took a little trying, but on its third try, we ended up getting selected. So that's it for my talk. Thanks for your attention.
Yes, thank you, Dr. Thyman. Okay, so moving right along, we're going to be doing our Q&A session now. Give me 1 second.
Hey, so thank you for the question and everything. And I want to kind of approach this in a couple different ways. So I kind of went over 3 different opportunities, right? We had the academia, which was really undergraduate and then graduate level. And then we also have like the research labs. And then we also have operational assignments. So the freedom that you have kind of depends on which job you're seeking. In academia, I could probably tell you that it'll be a lot of freedom. As long as your interests, your research interests align with whatever the scope of your job is, right? So like if it's within that job and it kind of applies to whatever you're looking
Okay, everybody, let's go ahead and get started here for our second round of presentations. This is going to be the tutorials and opportunities section. People pile in from outside to sit down. Nice. Thank you, thank you. Thank you, Berkeley boys. Okay, so our first speaker in the second round of presentations is going to be Dr. Tsuwei Fang. Dr. Fang is a space scientist at the NOAA Space Weather Prediction Center, focusing on the impact of waves, tides from the lower atmosphere on the ionosphere and quantifying the contributions of ionosphere variability from the lower atmosphere, solar, and geomagnetic activities. She received her PhD from the National Center University in Taiwan in 2009, and she served as a postdoctoral researcher at Ceres, University of Colorado Boulder, and NOAA Space Weather Prediction Center. She is the key developer of the coupled WAM-IPE model and leads initiatives at NOAA on space weather forecasting.
Thanks. Just give you a little bit more introduction with some updates. So I have been leading all the ionosphere-thermosphere activity at Space Weather Prediction Center. So anything you want to know about SWPC and what project we're working on and what opportunity we have, just come talk to me. I'll be here the whole week. So as you can see, what I'm going to talk about is what we're doing in Space Weather Prediction Center. It might be really foreign for you to understand what we're talking about, but basically what you learn, whatever field you're on, we look into it and trying to see if we can use that to improve our services. So, okay, next slide. Put enter. Sorry. So at Space Weather Prediction Center, we are located at Boulder. Our goal is safeguarding society with actionable space weather information. So as you can imagine, everything you can think of that you have studied and look at the sun, there are a lot of solar physicists in our building. There are a lot of people in different domains are working together in our office. And we are under the National Weather Service. As part of our mission is protecting life and properties. And I'm going to give the other updates on Friday, which is the other branch of NOAA. They are responsible for the satellite development to all the infrastructures and architecture for the satellite information we need for space weather predictions. But in our center, we do Space Weather Prediction Center, and we are one of the only center in the US that are leading the effort. And we work closely with, okay, so if you go to Space Weather Prediction Center, you're in Boulder, you get to visit us, that's how we look like. We look at the sun all the time. So imagine how boring that is in solar minimum. We really have nothing to look at. So our forecaster usually quit. There's nothing to do, but that's part of the job. And we have about 10 to 12 forecasters. That is, we have shift of 24/7. So we have forecast office running all the time. So when you're sleeping, somebody just looking at the sun all the time. So they capture flares, they capture any activities on the sun so that can protect us if something happened. And we also have a lot of collaborations among governments. So we work closely with Air Force. We work Air Force, Space Force. They also have a 24/7 office, 557, that work with us closely. And we have a liaison from Air Force in our office, like stick in, and they call each other 3 times every day just to talk about space weather activities. And we also work with NASA very closely, especially the Moon to Mars office, to support the Artemis missions when we're in the space, right? So, and these days, there are a lot more things that beyond NASA. We have a lot of companies will launch rocket. They'll call us in advance to figure out what's going on, SpaceX, Rocket Lab. So I think space weather is getting a lot of attention, mainly because solar cycle is approaching maximum, and we are predicting the maximum will be next year, about fall. However, the geomagnetic storms tend to happen a lot more in the declining phase of solar cycle. So we are not just like, okay, we're picked, we're done. So next 5 to 6 years is something that we are very important, and then we'll gradually go to the solar minimum. So when you talk about space weather, I think everybody think they're working on space weather, right? So a little bit of everything that we're studying right now. So what we really do is we look at sunspot. So our forecaster every day will name different number of sunspot. They look at the magnetic field structures of each sunspot and characterize the possibility of they have some activities. Then use all that to do a probability forecast, which is not super mature at this point. But what we are looking at are meant to event in the space. One is solar flare, and one is the coronal mass ejection, CMEs. And I don't know how much you understand the difference between them. Some of it you understand. I actually took many years to figure out the difference between all that thing. So what happened is solar flares erupt from the sun when there's a strong and complicated magnetic field structures. When solar flare erupt, he reached the Earth in 8 minutes because it come with a light speed. So usually we don't have a lead time to predict it. We don't know when it will come. Of course, there are a lot of solar physicists, they think they can predict it. But actually when we see it, it comes, right? So solar flare had impact on what? You guys have answer? Anybody know the answer? What a solar flare impact is? So solar flare impact ionosphere, especially in the E region and D region, right? So that communication, HF, COM, what FEMA needs, it's the first step. And then we also have CME coming right after that. So CME lead to what? CME coming with a particle, come all the way to the Earth. The reason why it's so hard to predict it is, first of all, we don't have anything to look at them carefully. So we have one spacecraft at L1, Lagrangian 1 point, looking at the sun, right? So you can't see a 3D dimensional of that thing, right? So you see an image, something erupt from the sun. You don't know if it's actually coming here because sometimes it can be off, sometimes it's going up. So the right direction is a problem. We have a lot of models to deal with that. And the magnitude and the magnetic field structures, right? So if you come, the magnetic BZ is going northward, you actually don't have impact because you're parallel to the Earth magnetic field. So you got to really have a strong BZ that going southward to have that reconnection impact. So sometimes when I know things are coming, actually last storm, one of the big one, I was sitting there 7 hours just looking at solar wind. That Sunday, I was just looking at solar wind parameter for 7 hours, just keep on updating it. But until that KPA hit, and I know that's coming. And that's embarrassing because when we talk to SpaceX, they're like, how come you don't know it's coming? I said, I told you 3 days ago it's coming, but I don't know exactly what hour it's gonna hit and how big it is. So I think there's a lot of room to study this and understand the impact of space weather. And we really don't know as much as we think we know. So there are a lot of things to study. And I think many of you have seen this animation from NASA. That was a good one. Like you can see that when solar activity is strong, magnetic field structures, complicated one will start to have flare. Sometimes flare come with CME, sometimes flare doesn't come with a strong CME. So we really need to use some of the measurements between sun and the Earth to actually characterize the activities. So once the magnetic field hit, the solar wind parameters, solar wind structures interact with the Earth's magnetic field, you start to see a lot of magnetic field structures and reconnections. And we talk about the aurora and high latitude activities. That's the whole system that comes to the Earth. And what is CEDAR community's effort is to understand what comes next, right? So whenever there's a storm, question to me is, okay, what happened? What's going to happen? So how do we capture that? We use a lot of ground-based receivers to look into it. We use satellite to look into it. We use the model to run into the future. Hopefully, we can capture a lot of them. And then the only thing you can see in space weather is aurora. So a lot of times when there's a storm, the most media request is where is the aurora going to be? And I told them, don't come to me. There are so many other scientists in the center who can deal with it because I really don't want to go. And the recent one, I got a Fox News. They're like, do you want to go to Fox News to talk about aurora, where you can see aurora? I said, not really. It's not something I'm really into it. But this is the one that gets attention of the regular society, right? So last storm, I think they see a lot all the way down to a lot of states. And we can see that in Colorado. We were seeing that in Colorado as well. So I think there are a lot of science behind the aurora, and then there are a lot of experts in this community can tell you how that works and under what conditions you can see different aurora. But that's certainly not my strength. And I'm not willing to go to a national channel to talk about aurora on that. So, but that's a huge things that getting people's attention. And subsea, there are 3 skills that we currently provide day to day, and we are thinking about evaluating that. One is the R skill. That's a radio blackout skill. So we have skill 1 to 5. 5 is the worst one. And that's really a solar flare impact. So solar flare comes, what frequency gets short out. Sometimes the polar region, the frequency will have to change just because the response of the proton event that come right after flares. S skill is solar radiation storm. That is solar radiation storm warnings, mainly for the aviations. We are trying to see how we can improve that for well, that's for aviation communication, I'll say it that way. But we have recently getting a lot of engagement with the aviation industry, trying to understand the radiation impact on human. So the pilots and the crews are really worried about radiation impact on their day-to-day life going through the polar route. And we also have a G skill, that's a geomagnetic storm skill. That is the reflecting of the CME and like Corona Hall recurrent of those features. So that's a geomagnetic storms that we're talking about. So a lot of times we get called, they're like, oh, this is bad because they say communication going to be out, GPS will be out. But a lot of times they are a very rough guide, but these days, because the private sector is growing like crazy and people don't understand that they're over reading our skills. So we're trying to see if we can improve those skills and improve our alert system so that can be tailored into different system. And there are a lot of impact for space weather. So that's making my life difficult because we have to deal with all this all the time. So they can have impact on satellite operations, like what? Radiation impact on the spacecraft, single event, and a lot of different charging events. Those are something we get called on, why this satellite is off, why this satellite is charging. So how the radiation environment is. The drag is a big problem I'm dealing with because we are getting maybe more than, we have a lot of satellites. Every company I talk to have 300 satellites. Every company started aiming 4,000 satellites. So that is a big problem, and we're trying to figure out how to do a better job, understand the drag, thermosphere density, and how do we help with the collision avoidance and space traffic management. And we also do space flight, human space flight, and not just NASA astronaut. There are so many companies start to have those space tourism. They all come to us and say, okay, we need some education on that. So I think getting a lot of knowledge is really important in this era. So human space flight, the radiation impact on the humans, on the instruments and everything. Aircraft operations is also very important. So why does it, have you ever thought about space weather impact on aircraft operations? I mentioned the spacecraft radiation impact on humans. That's one big activity that we're going on with the aviation industry. The other important thing is they use GPS guidance system to land. And then how do we make sure space weather impact is not impacted the positioning and all that. And also the other most important thing is currently all the international flight still rely on HF communication on the ocean. So we do work closely with some of this traffic control center to identify the impact. And a lot of times they told me that we just shift to SATCOM. And then they didn't realize that, yeah, SATCOM can also get an impact when you have a severe simulation event or a lot of jamming these days. We often see a lot of signals that have nothing to do with space weather event, but jamming and spoofing. So trying to see how we can identify those different impact. And railway and power grid companies, those are one of the big things that has been dealt with in the highest level, like in White House. They've been dealing with that, make sure everybody's electricity doesn't get interrupted when there's a big space weather event. And of course, the GNSS and GPS, like all your phone, when you're going everywhere, we're receiving GPS signals, right? So ultimately, if we can maintain spacecraft operation, a lot of things will be impact in the loop. So I think there are a lot of things that we are trying to identify, what is the biggest economical impact that we need to focus on. And then if you go to what do we do as subsea? We have a lot of different models. So we have, I lost my screen. Go back. Space weather event. So maybe something. We actually have big flare in the morning. We have an M-class flare in the morning. Anyway, so there are a lot of different models to capture. I'm going to jump it, so you don't need to deal with that. But there are a lot of models from sun to the earth that help us to do our daily job. So we have a model called WSN-LL. If you heard about that, that is capture the solar eruptions and how the solar wind propagation to the earth. Then we have a model called Geospace model that was provided by Michigan, University of Michigan, that go from Lagrangian point to capture some of the magnetic field impact or the KP predictions and the electrical grid predictions. That is the Geospace model. And one IPE model that I have deeply involved in the past decade was to capture this. So you must have seen that. So our goal is to capture everything, right? So everything from the sun all the way to the earth, we want to capture that. And we also have, probably have to go back to the flushing slide. Oh, it's working now. Oh, it's not working again. So, okay, so we have a Carry 7, that's a radiation FAA model that we really want to understand the radiation on the aircraft flight levels. So for one IPE model, and you're going to hear we have postdoc students and different research group has started utilizing this model to do our research. The goal is to capture everything in this plot, right? So you have the yellow arrow for the neutrals. So you want to understand the heating, you want to understand the tides, waves, wiggles, and everything in the thermosphere. And how does that interact with the ionosphere, right? All the equatorial regions. That's why it's kind of interesting now. You go to CEDAR, you're like, they're all separated, but our job is to combine all of them together and make sense out of it, right? So that's why Space Weather Prediction Center is not just taking care of the solar drivers and the activities on the Earth, but also deal with this, right? This is from Jeff Forbes' plot that we want to build model that capture gravity wave, planetary wave, and all kinds of wave you can think of. And we also want to capture aurora and the impact of the aurora and all this draw heating impact during the storm. So I will say not just looking at the sun, because we started to realize that a lot of the research has indicated that a lot of change from the lower atmosphere have significant impact on their upper atmosphere. So how do we really capture different aspects of what we are studying from the sun or from the ground and impact the weather in the space is something that we are emphasizing right now. And then some of you might have seen the slide. I have been emphasizing that this is the three things, actually only three things that I'm looking into right now is how to do a better job capturing the impact of HF communication during storm time or quiet time where there's a severe meteorological event. And how do we do a better job to help the satellite industry to do the satellite positioning, navigation, timing, and communication, the GNSS aspect of the problem. If you're studying ionosphere simulations, spread F, and all that folding into the second category. And if you study bottom side ionosphere, E-region, HF communication, that's the first one. And the third one is the satellite drag, right? So if you're studying data simulation, thermosphere density data simulation, if you're studying astrodynamics, that's the third category. But you can see that it's a widespread range of study and emphasis we're doing. I'm probably gonna give you a little bit feeling of what we do in terms of model. So one might be model, I talked about it. We build a model from scratch, not from scratch, but based on the weather forecast model 15 years ago. So we built upon the weather forecast model and expand the model all the way from 60 kilometers to 600 kilometers. And then we have to include the plasma processes, just like some of you might be using Wacom, right? So Wacom X is sort of similar type of model, but it's not built on the NOAA system. So we want to include all the weather models and all the weather systems and ionosphere-thermosphere processes. And the model currently produces a three-dimensional field in real time, which means it's running all the time. So my job and my team's job is to make sure things doesn't crash. Luckily, we start in July 2021. It has not stopped one day ever so far. But that's just not just that. When you're talking about one model, it's not operation, right? It's just a numerical model. And we know we all wrote in Fortran. So it's not very easy to be used in current software engineer. They're like, what is this monster? So we have this model. We have to package with the workflow. We have to package with extra stuff to make it operation. So you might have heard something like this, CONOPS. So what is CONOPS? It's concept of operation. right? So right now we have CONOPS 1 in operation since July 21. We're implementing CONOPS 2. So the reason why we want to do CONOPS is to understand what is going to the model, what is coming out of the model, what kind of real-time capability we're looking for. So beside, not just the model itself. So for example, CONOPS 1 is the date, like a weather model. We run the model 4 times a day. Every 6 hours, we run the model 2 days in advance. So every 6 hours model will run 2 days. Why is it 2 days? Because we only have KP forecast for 3 days and the model doesn't run fast enough to go to the 3rd day. And nobody used the 3rd day anyway. So we decided we'll run the model for 2 days. So every 6 hours, the model run 2 days. But that is not sufficient to capture a storm, right? A lot of times, and pathetically, last storm I was looking, the model just doesn't have storm when storm is on set. So we need CONOPS to capture storms. So now the model we're going to run every 5 minutes in real time from maybe a month from now. So 1 month from now, we should have that CONOPS coming. And not just that, you're thinking about research, you're thinking about getting things in, you're thinking about drivers, and you need to make sure the driver is good, right? Our solar wind data is crappy. It's always bumpy and always no data. We only have 2 spacecraft there. Sometimes you don't have any data, so you have to make up something in between so that the model doesn't just stop. So I think there are a lot of constraints when you go to the readiness for the operational model. And then because there's so many satellite industries coming after us, so we started releasing neutral density source. So the first one is coming, we have some help from NASA CCMC to provide that data set. You can go download all the models, outputs, ionosphere, thermosphere, it's all there. So if you have any research objectives, you can use that data set. And that's all come from our operational output. And second one, and you can show me how bad the data look like. I'm really encouraging everybody to tell me how bad things are, because only getting that guidance, we can move forward. And the second one is we are starting to have our operational output that kind of give us mainly the neutral density specifications, and it's like cloud systems. You can go download the 4-dimensional, 3-dimensional density, neutral density, if you are interested in satellite drag estimations. And then the other thing that we're doing, and a lot of people at SWIPC doing, is the customer engagement. So we often talk to aviation industry. So we had this test bed experiments last year that we have our team operation and research coming in, and we have major airlines, United, American, there are several airlines coming, Delta. And then their air traffic management group also coming, tell us what they're doing day-to-day life and what do they need from us. And we also have many partners coming from NASA, and NSF as well was there. And we have other ops team coming from UK, Canada, and other scientists from US. So I think the goal is trying to get this and try to understand the requirement, right? So why do we do this if nobody cares, right? So we want to make sure whatever we do has a sufficient impact. Some pictures from our last year, but this was really limited. We are like 50 people counts. We can't have more than that. And we run a satellite industry engagement during our space weather workshop this year. On Monday, we do a 4 to 5 hours engagement, and we have surprisingly all the company just show up. Every company show up, and we have SpaceX, we have Amazon Kuiper, and all of them really worry about where we are with the drag estimations and collision avoidance. And then the problem that we're seeing right now is they don't have the same tool. So imagine that everybody has different tools at this point. And we are very lucky nothing's hitting each other at this point, but with more and more satellite going up, NOAA also have a responsibility to manage the space traffic management and provide all this collision avoidance message. So this is my last slide. The other thing I want to emphasize that at the government level, we work very hard on trying to transition everybody's work into operation, right? So how do we do that? Because a lot of times your work will stay in readiness level 1 and 2. So it's basic research, applied research, and how do you get to a mature level to be operation? So ultimately, why whatever you're working on, how do we get to have an impact on a society, something that we are working on? So NASA has this R202R grant that facilitate that activities. Then if you're interested in that, I have a session tomorrow, just talk about this thing itself for 2 hours. So we can all talk about different projects we're working on and what's NOAA, NASA, NSF is looking for, and how do we try to improve this process in the future. That's all what I have. Thank you.
And Dr. Feng, I think we have time for a few questions, if that's all right.
Yep.
Okay. So guys, you can submit your questions to Slido as usual. And the first question is going to be, I have heard that the NOAA space weather severity scales are changing. Do you have any information on what the new scales will be / improve upon?
The new scale for,
Yes.
I don't have that now.
Okay.
This is still in very early stage. Severity scale. Okay, you gotta come and tell me about the rumor. What does it sound like? Because I don't think I know what's going. We're changing, but nothing is solid at this point.
So the second question is, how can the CEDAR community help with the outreach and education? We have a lot of experts who could help with this.
Yeah, I think that's actually what we really need help with, because I have so many people contact me. They want to learn about space weather. I actually told people you can just open a company, just teach about space weather, you can make money out of it. That might be some business idea you can think of, but we actually, so we don't really know at this point how we do that, but we actually trying to kind of team up with NASA, like CCMC, Goddard has a lot of experts, and then NOAA has a lot of experts and help us to do that training. Because I don't really want to go talk about space weather for 5 times every week, right? So I think there's sufficient need. And then training our forecasters so that they can talk to the customers is probably the key. And we're job open. So we have federal position open for forecasters, and within our center, we have 40% vacancy. So we're going to hire like crazy in the coming few years for federal positions. Yeah.
That's definitely good to know. So for NOAA, how important is the impact on the general public versus industry stakeholders? What, if any, forecasting products are directly tailored to the public?
So when we talk about general public, I will assume we're talking about the government process, because we all rely on the government to run day-to-day life, maintain the road and things for us. So we work really closely with the government sector, FEMA, I keep on saying FEMA, but there's so many government agencies that we work with. But these days, it's just the industry is growing like crazy. So our product certainly is not sufficient to be used in their activities. And we don't have that kind of support. We get called all the time when something happened. So I think it's important, it's impactful, but in terms of how we really don't do tailored services at this point, because there's no way. For example, there are a lot of people coming to me and say, let's put a warning for satellite drag. I said, where do you want to put? 200 kilometers, where SpaceX released their satellite, 300 kilometers, 500 kilometers, 800 kilometers, what orbit you're talking about. So I think that is just not feasible for us to do that. So maybe provide more and more information so maybe people can do their own tailored services will be the future.
Yes, thank you. And so our next question is the SWPC S scale also relevant for those astronauts and spacecraft radiation impacts, or would that be a separate type of alert?
Oh, I think that's where the rumor comes. Yes, we are trying to separate the radiation, because right now the radiation S scales really for radiation environment for maybe spacecraft and different thing. So now, the severe, like the threshold for impact to humans and things will be much higher. So that need to be changed, and we are thinking about how we change it.
Okay, Dr. Feng, I think we're out of time for this one.
Yeah.
Thank you very much.
Yeah, just come find me.
So our next speaker is Dr. Alan Liu. Dr. Liu is currently serving as the Geospace section head for the Division of Atmospheric and Geospace Sciences at the National Science Foundation. He received his PhD from UIUC in 1996 and has been a tenured professor at Embry-Riddle Aeronautical University since 2015. His research interests include middle upper atmospheric dynamics, composition, and chemistry, as well as remote sensing techniques. So without further ado, let's hear from Dr. Liu about some information from regarding the NSF.
All right, thank you. All right, excellent. Thank you so much. Right. Hello, hi everyone. Okay, let me try. Okay, what about this? Okay, yeah, so my name is Alan Liu. So I'm really glad to be here at the CEDAR. I've been in CEDAR attendance for many, many years. So I'm currently a rotator NSF and manage the Geospace programs. So today is the student day. So many of you are graduate student and early career scientists. So I thought I want to talk generally about what NSF really is and what we are doing and how you can, participate in NSF activities, writing proposals. Many of you probably will do that sometime in the near future, right? So first of you, for this talk, I want to talk a little bit about history. So how NSF was actually established, because that actually relates to why we're doing what we are doing now. So this is near the end of World War II, and the government realized the importance of science that really played a pivotal role in the outcome of the war. And so President Roosevelt wrote a letter to the then director of the Office of Scientific Research and Development, which was an office in the military, actually, responsible for developing a lot of research to support the war activity. So asked Dr. Bush to create a report on how we are moving forward to support science for the country. Okay, and the outcome of that is his report called "The Science: The Endless Frontier." You can find that book. You can Google it, and I did that. Actually, I found this book actually is nearby in the University of San Diego library. There's a book of that. Okay, and that's Dr. Bush and the front of that book. And in this book, there was a main point that it envisioned that a new agency need to be created to support basic science for the country. And a few years later, Congress passed a law called the NSF Act, and that's the start of National Science Foundation, together with the National Science Board that oversees the activities of National Science Foundation. Okay. So this is the National Science Foundation Act of 1950, and that's the start of National Science Foundation. And you can see the beginning of that act says that the mission of National Science Foundation is to promote the progress of science, to advance national health, prosperity, and welfare, and to secure national defense, and for other purposes. So that is always been the guidance of the National Science Foundation's mission. Okay. Okay, so a little bit about the National Science Foundation organization. This kind of chart may be, confusing or something, but it's actually quite relevant if you are going to write proposals to NSF. Okay, so NSF, under NSF, there are many directorates, and these are the 8 science-related directorates. There are other units at Science Foundation. But these 8 are the, you can see it covers different disciplines of scientific research. So GEO is called Directory for Geosciences, is where most of this, community, research in this community involved with that. Geosciences is any research that related to Earth, okay, the life, the bioscience, the ocean, the geophysics, and our, CEDAR science. The bottom one, TIP, is the newly created directory. So many of you have heard of. That's called Directory for Technology, Innovation, and Partnership. That is somewhat different from the science disciplines. It emphasizes on translate the science into something that will have societal impact. Okay. Okay, so under our Geo Directorate, we have several divisions, and the division that this research committee is mostly related to is the atmospheric and the geospace sciences, so AGS. So under AGS division, we have 3 sections: atmospheric section, geospace, and another section specifically for NCAR facilities. So under geospace section, where I'm at, we have 5 programs. And 3 of these are core programs: aeronomy, magnetosphere physics, and solar terrestrial. And each of these programs has a specific focused solicitation, and CEDAR is on the aeronomy. Okay, and your sister programs, GEM and the SHINE, respectively are under magnetosphere physics and the solar terrestrial. Okay, so these are the 3 core programs, but we also have a geospace facility program that specifically support ground-based instruments. And we also have a space weather research, like Tue just mentioned, because the space weather is a activity that actually cross all 3 core programs. Actually, in addition to other programs within NSF as well. Okay, so that's where we are. That's where CEDAR is at NSF. Okay, so when you submit research proposals, you can submit it to any of these programs. You can submit to CEDAR focus program. Many different programs you can submit to. But for those of you haven't write proposal to NSF, this is a document that you always want to start with. That is called the Proposal and Award Policies and the Procedures Guide, PAPG. Okay, and the NSF usually update this every year, so there always be some changes. The document is really long, but you don't have to be intimidated by that, because if you start writing proposal, the part 1, chapter 2 is the main thing you want to look at. It's about proposal preparations. Okay, so you need to get familiar with that. So that's about the PAPG. Okay, so how we review proposals. NSF review proposals based on 3 principles and 2 criteria. The 3 principles, of course, first, it has to have high scientific impact. And the second, it needs to have societal impact, achieve societal goals. Because if you go back to the NSF Act, that is what NSF's mission is. Okay, it's not just for science, but it needs to support the national health and all that thing, etc. Okay, and the third one is that the awards have different sizes. So the merit of each of these depends on the award size as well. Of course, with larger award size, you can do more things. Right? So the 2 criteria, intellectual merit and the broader impact. If you ever write proposal to NSF, you probably already know all of this. So these 2 things are, all will be fully evaluated. It's not like one is more important than the other. But in practice, of course, the thing you often start with is intellectual merit. You're thinking about how to justify your proposal to be scientifically important, and you can solve the problems. But I want to emphasize again, the broader impact is very important, as you see again from the beginning of the NSF Act. Okay? And we always emphasize that as well. Okay, so broader impact has always been maybe more challenging aspect of proposal writing. So I want to just list a few examples of broader impacts. The broader impact actually can be very wide, and NSF doesn't really want to prescribe any particular activity on broader impact. So these are a few areas that you can think of. You can make your research environment more inclusive, and you can enhance STEM education, STEM workforce, or improve infrastructure, create partnership, and outreach, more public engagement, or improve national security. So there can be many different areas that you can include in your project as a broader impact. Okay, so I want to explain a little more how NSF, this funding opportunity works, because this could be maybe a little confusing. So generally, there are 3 categories. Programs I already talked about. You see aeronomy, magnetosphere, and all that, right? So programs within NSF is kind of a standing funding that's always there, that just specify a particular region or topic that anyone can submit a proposal to. Okay, it only have very general proposal requirement. Okay, following the PAPG, right? But we also once in a while issue this thing called the solicitations. Solicitations is more specific. It usually have a specific funding level for a specific purpose, and sometimes it has additional requirement that's on top of the PEPG. Okay, so that is issued, once in a while to fit a particular needs, from the, that we see as a, research gap. And the third one is called the DCL, Dear College Letters. And these are used to express NSF's interest in receiving more proposals in particular area. It does not necessarily come with specific funding amount, but it will be useful to pay attention to this because if a DCL get a very healthy response, it may turn into a solicitation. Okay, sometimes it could also be the other way around. If there is a solicitation, we could also have a follow-on DCL to explain more about the solicitation, to answer community questions. So these are the three ways that we explain funding opportunities. Okay. So because this is all mostly early career scientist, graduate student here, I will highlight a few opportunities. So graduate research fellowship program is a standing program, so it's always there. It's a fellowship to support a graduate student. This is the NSF wide competition, so it's around January. I think it's being reviewed. And the senior level undergraduate student and early year graduate student all qualify. Okay, so you do have to be a U.S. Citizen or all residents. Okay, and if you graduated, this is a postdoc fellowship opportunity, and this is also NSF wide, but every division or directorate have their own specific requirement. So that's why, AGS, our division, have our own specific postdoc research fellowship solicitation. Okay, and in this particular solicitation, we just recently make update with this amount of support that increased from the past. So now it's 100K to 102K, over a 2-year period. Okay. So go further down the road, if you're interested in the academics and you want to become a faculty member, this is a brand new solicitation that we just released. This is called the Faculty Development in Geospace Science. The goal of this solicitation is to incentivize institutions to create a tenure track position in the space science area. Okay, it's not for existing faculty members. So we want the institution to create this position and hire a new faculty to then support this new faculty member to integrate the geospace science research into the institution's entire curriculum. Okay, so it's a $1.5 million up to $1.5 million over 5 years. Okay. And then there are many other things, and many other opportunities in SF that I want to describe all of them all. But here the career award probably many of you know, and we have some career awardees here. So this is a very prestigious award that support tenure track assistant professors for up to 5 years to develop their career throughout this research activity supported by this. And the second one on the eclipse is showing that how we are flexible in adapting new research needs. We all know the eclipse is coming up, annual eclipse in the coming October, and then next April we had the full eclipse across the US. So we have a DCL that asking the community you can request a supplemental funding or new proposal to do specific work related to eclipse. Okay. And then we have the CEDAR solicitation. Of course, that's the solicitation that actually support the workshop and all the student, the travel, everything that's all supported through NSF, through this. Okay. The last one I also want to mention is that we always recognize that the underrepresented groups that are not as well supported by the NSF. So we always look for enhancing the minorities or underrepresented groups. So this is another Dear College letter that we express our interest in providing additional support to those institutions. Okay. Okay. So I guess are there other slides? Okay, I think that's okay. I have a couple of slides I added this morning, but it's not showing up here. But anyway, I can just say that. So the main message here that NSF is a funding agency that support basic research, support curiosity-driven research. Okay, this is very different from like a NASA that has a mission-driven, and then NOAA have their own mandate that needs to provide forecast. So because of that, NSF is very flexible in deciding what kind of research to support. And we have not only those proposals that's reviewed by external reviewers, but we also have other opportunities like called the EAGER that can support those more drastic ideas, but can potentially very transformative idea. So those high risk ideas we can even determine internally without external review, okay, to fund those activity as well, okay. And also there was a comment earlier about the lower fund, difficulty in get funding and all that. There is NSF has a website called NSF by numbers. So if you are interested in that, you can look at those numbers, see what the numbers you are interested in. But I want to highlight two things: is that the funding rate, which is the awarded number versus the proposal submission for Geo, has been increased in the past 10 years. Okay. And also the award size has also been increasing in the past 10 years from about 100K to about 170K, okay, per year. Okay, this is median award size. Okay, so that's the current situation. I also want to mention that the funding at NSF is largely driven by the community needs, community interest. Okay, so it's not a top-down approach. NSF, we don't have like an in-house scientist to decide what needs to be done or what is not. We are there to support the community with the best research ideas, science ideas. So really, if you like to see what needs to be done, what's important for the science or for the education, please participate actively to all those community efforts, such as the most recent, decadal survey. I know many of people in our community are contributing to that. So that's all great. Okay. And finally, I want to say that NSF always rely on reviewers, external reviewers to process our proposals. So many of you, once you get your degree, PhD, please contact us at NSF, volunteer to be reviewers. And that is really, really important. And for us to do our job and for serving your peers. Okay, so this slide, this shows pictures of all of us. So we are not really abstract, just an email behind the scenes. 4 of us are actually all here at the CEDAR meeting. So myself and Tai-Yin Huang and Shika Rizzo is the new aeronomy program director, as well as Roman McCurry, which managed the Geospace facility. So 4 of us will be here at the meeting. Please talk to us, okay? Any questions, or even you don't have questions, we also are very happy to get to know you, right? Okay, so that's all. Thank you very much.
Yes, thank you, Dr. Liu. And we actually have a few questions if you have a couple minutes. So the first one is the AGS proposals are accepted at any time, but are they also awarded at any time, or are they only reviewed and rewarded once a year?
Right. So the answer is both. So for example, the aeronomy program can accept a proposal anytime, so there's no deadline. The CEDAR solicitation has a target date. Target date means we have a date that we expect to receive all the proposals, and we'll typically review them together. But for programs that have no deadline, sometimes we use ad hoc reviews, which means we individually get the reviews and then make determination individually instead of ranking. So we choose this different method based on internal situation. Okay.
Yes, thank you. And the next question is, on average, how many applicants do you get for the GRFP and or the AGS postdoctoral award, and how many are actually funded?
So how many awards you can easily search on SF award website. I can say that the GRFP award in general, the AGS or even geoscience has a relatively smaller percentage than other disciplines, engineering or computer science. So internally, we do look for ways to try to balance that. So relatively, I may say that this particular fellowship itself is very competitive, but for geoscience, it's a little bit we are looking to fund more of people from geoscience.
Yes,
right?
thank you. And the next question is, are there opportunities to work directly for the NSF in some capacity?
I'm not sure what mean working directly. So maybe two aspects. One is, again, we really welcome volunteer reviewers. You can once you serve as a reviewer or on the review panel, you can see how other proposals are written and how they're viewed by their peers. Okay, so that's very helpful for you to write proposal. And on the other side is like myself, is a rotator NSF. NSF is kind of very different from other federal agency. It has a very large number of rotators. Rotator means that these are usually scientists work at NSF on a temporary basis. Okay, so it's not all civil servant and permanent people. So that this group of people can always bring new ideas to the agency, and has a limited, typically 2 to 4 years term at NSF. So that's also something you can look out for opportunities. So that'll be directly, working at NSF.
Yes, thank you. And so we got 2 more questions left. And the first one's going to be, if you are awarded the GRFP, are you still eligible for the AGS postdoctoral award?
Certainly, yeah, there's no conflict at all. I mean, that's, it's a one, and one is for graduate student, one is for postdoc, right?
And the very last question is, does the NSF collaborate with agencies from other countries to determine the value of a scientific investigation?
Yes, very much so. So depends on the interest of each country. That NSF have a specific directorate working on international aspect, and even internally as a Geo Directorate, we often also reach out to other funding agencies in other countries to see if there's an opportunity to collaborate. And once those are identified, then we will create some, either DCR or something, or some mechanism to fund, to co-fund the project. One typical way to fund it is that such a proposal will be reviewed only by one country's funding agency. And then, if it's reviewed favorably, then both countries will fund it.
Yes, okay, thanks again, Dr. Liu. And okay, it's been a long morning. We're going to take an hour-and-a-half break for lunch, and we'll be back at 1:45 to continue the tutorials opportunities section.